station of 7 people and 5 visiting vehicles. That will turn into 6 tomorrow. As Murray mentioned, a full parking lot, home for the holidays.
Dragon separation confirmed.
And with second stage separation confirmed, Cargo Dragon is now flying free on its own, continuing its journey to the International Space Station.
Watch the food. Drop it down. Drop it. Turn it up. Now, we just gotta clean it out before it's in.
Got brand new guns.
He's just getting upset. We can't get him tortured. Drop it. Turn it up. Now, we just gotta clean it out before it's in.
Got brand new guns.
He's just getting upset. We can't get him tortured.
kids. What's the big thing you're working on and working towards?
Yeah, I teach at university. I'm a professor, but I also use Skype. As soon as Skype was invented, I thought, wow, I can just sit in a classroom with kids with no overhead, like there's time, and we can have a chat. So I started that back as soon as Skype was invented. I did it at lunchtime, called it On the Lunch Pad. And so I... real dangers of life. How do you deal with catastrophic loss? How do we as individuals get outside the little confines of our normal life and be ready for the real broad complexities and richnesses of life? And when you push people right to the limit, sometimes that's where you experiment not just with the hardware, but with humanity itself. And to me, that's a large part of exploration. It's not just physical exploration, but it's also human exploration. And so I speak all over the world on those ideas as well, because in amongst all the fun technology and playing music, I think the real value is in helping as many people as possible look at what they've done so far in their life, think about some of the possibilities that they haven't got to yet, and maybe make a few new decisions about where they might head next.
Right, and possibly space flight, which brings me to ask you, do you think you'd ever go to space again?
I'd love to fly in space again. Here at the Kennedy Space Center, I was standing next to Atlantis very recently, and that was amazing. Sure, I would go for a ride with no purpose. Imagine if someone pulled up next to you with a nice new, Corvette and said, "Hey, want to go for a ride?" And you said, "Yeah, sure." And you went around the block in the Corvette. And then he came back and the next day said, "Hey, want to go for a ride?" You're like, "Okay." And then came back a third day. After a while, like, "Okay, I've already had a great ride in that car, but what are we going to do with it this time?" And that's sort of where I am in space flight, is what would be the purpose of it? The ride itself is titillating, but what are we going for? And where, what purpose does it serve? And
right.
I would love to be involved with the team that is figuring out how to successfully build a station around the moon and the first settlements on the moon. To me, that's a huge, interesting challenge, not just going for a ride. But yeah, if you're offering, sure, I'd love to go for a ride.
We've got some rockets and spacecraft around here, Chris.
I'd love to.
We'll see what we can do.
Sure.
We appreciate you so much taking the time to be here, not only to enlighten us with all of the projects you're working on, but also playing for us. It was truly a treat to have you.
My pleasure. And you need to bring 2 guitars so we can play together next time.
I'd love that.
All right.
Chris
Thanks.
Hadfield, thank you. I'm Daryl Nail, and that's our show. Thanks for stopping by the Rocket Ranch. And special thanks to our guest, Chris Hadfield. To learn more about Chris and all the exciting projects he talked about, you can go to Chris Hadfield, that's HADFIELD.ca. And to learn more about everything going on at the Kennedy Space Center, go to nasa.gov/Kennedy. And we've got other cool podcasts you'll find at nasa.gov/podcast. A special shout out to our producer, John Sackman, our soundmen, Lauren Maythree and Isaac Watson. And as always, remember to keep looking up.
Let's hear it for the world-class NASA STEM Stars team. From NASA centers across the country, we present Hannah Kaplan.
Hi, everybody. I'm Jen Hudgens, coming to you from the Kennedy Space Center, and welcome to this week's NASA STEM Stars episode, where we get a chance to talk with NASA subject matter experts from all over the agency and ask them questions about their jobs, their careers, and backgrounds, and dive a little bit deeper into a STEM field. Today's special guest is from the OSIRIS-REx mission. Her name is Hannah Kaplan, and she is a project scientist. So I'm really excited to have Hannah here with us today. I just wanted to let you know that if you have any questions from Hannah, you can drop those in the chat window. And just a brief agenda for today, we're going to chat with Hannah, talk about her career, and you're welcome to ask questions all along the way. We're going to learn about the OSIRIS-REx mission, and then I'm going to challenge you to an activity of that goes along with today's mission. And then I'll tell you about next week's episode with the James Webb Space Telescope. So welcome, Hannah. Thank you so much for joining us today. How are you?
I'm doing great, Jen. Thanks for having me.
Absolutely. So you're with the OSIRIS-REx mission. I cannot wait to hear more about it, to tell students more about it. But can you tell us a little bit about how you got to working at NASA?
Yeah, absolutely. So I have a PhD in planetary science. And so that's the most immediate kind of step to NASA. But I really came directly from this mission. So I was working on the OSIRIS-REx mission, and that is what led me directly to take the position I'm in now at NASA. But I can step back even further than that if you'd like.
Yeah, absolutely. So tell us a little bit about yourself. What are you interested in? What are your hobbies?
Yeah, so I am really interested in baking recently. I've been making a lot of bread. This seems to be a common quarantine activity, but I've been really enjoying it. I love to go on bike rides. I just started a fall vegetable garden, which is dying, but I'm really hoping that this spring will be more successful. And of course, because of what I do, I happen to also really be into meteorites and asteroids. We could call that a side passion, or, my day job, perhaps.
How did you get interested in meteorites? Did you find something when you were younger, or were you always a rock hound like me? I love rocks. So how did you become interested in geology?
Yeah, so like you, I came in through rocks. I really loved rocks. Not starting so early in my life. I think I liked to collect things as a kid, and rock collections are a really nice thing to collect. But in college, I really got into geology as a study, and that's, I started looking at rocks on Earth, and that eventually, along the way, led me to look at rocks in space. And so meteorites are really cool because they're chunks of space rocks that we have on Earth that we can actually look at and study in a lab. So it's kind of like the best of both worlds.
So you're working at Goddard Space Flight Center in Maryland, right? So did you grow up in Maryland, or where did you grow up?
So I actually grew up on the island of Bermuda until I was about 11 or 12, and then I moved to Lexington, Massachusetts, where I did the rest of my middle school, high school education there at the public school system. And yeah, so that I'd say the first time I remember doing science was probably in Massachusetts.
And then where did you go for your undergrad and what was your major?
So I went from there to WashU in St. Louis, and I was an Earth and Planetary Science major. And so I went in through a program called the Pathfinder program, which was run by Dr. Ray Arvidsson, who had this program that was aimed at environmental studies, maybe with a crossover of some geology. But he himself actually was heavily involved in the Mars rover program. And so that's really where I got into planetary science. And I started and I joined this program because I wanted to be outside. I wanted to be hiking. And I thought that, geology, environmental science, that seemed like a cool way to be able to do that. And I kind of fell in. I met the right people there and started doing research, not in the field on Earth, but in the field on Mars.
So it sounds like that professor was a mentor of yours.
Yes, and that has been, I'd say, the most important part of my career has been the series of mentors that I've had along the way. And so I'd say really starting with Dr. Arvidsson, who was a big influence on me, and then moving to my PhD advisor, Dr. Ralph Milliken, and then a few people on the OSIRIS-REx mission like Dr. Vicki Hamilton and Dr. Amy Simon, who all of these people have really taken me under their wing and allowed me to succeed and shown me how to succeed. And I think that, if I were to give anyone advice in terms of what they should do to be successful, in science or maybe anywhere, it's, find those people who are going to help you and, guide you on that path. And I've been very lucky in terms of the people that have done that for me.
So how did you get interested in pursuing a PhD career? Did you, after your bachelor's and college work, did you do any internships or work between the two, or did you directly go into studying for your PhD?
Yeah, I took what we'll call the straight and narrow path. So I went immediately from undergrad. One day I was doing research in the lab at WashU, and the next day I was working in the lab at Brown, which is where I did my PhD. And, I've met people who have done this all different ways. And I think, people who don't go straight through to PhD have these incredible experiences that can really help them with their research. For me, by the end of undergrad, I was convinced that I wanted to do research. It was what I loved doing. I wanted to stick with the projects I was already working on even. And so it was very easy for me in terms of, the deciding the next step. It was very easy for me to go to Brown and to join a lab group there and to continue my research.
So you're a research scientist, and that last picture on that slide we just saw says OSIRIS-REx, and the NASA symbol is there. So you're obviously working at NASA now as a research scientist, but can you explain to us what OSIRIS-REx is and why a planetary scientist should be working on that program?
Yeah, absolutely. So at Brown, as a planetary scientist, I was studying meteorites by the end of my PhD. And I was specifically studying meteorites that had a lot of carbon in them. And so OSIRIS-REx is a mission to an asteroid, and the asteroid is called Bennu. And we think that this is a carbon-rich asteroid. And so the rocks I had been studying on Earth were really relevant to this mission, as it turns out. And so a lot of my expertise in looking at these rocks, especially looking at them remotely with a spectrometer, that's kind of what I do, that is what made me a good candidate to go then work on this mission. And so I think, planetary science involves not just strictly planets, but also people studying small bodies, comets, asteroids, and meteorites. So you get a lot of variation there.
Very cool. So can you explain more about what a planetary scientist does?
Yeah, so I'd say my job, especially now that I'm at NASA, is highly, highly variable. So here on this slide, I show 3 different things that I'm involved in to some extent every day as I work. So the first is instrument science. And so this is one of the newer things that I'm involved in with my position at NASA. And with all new things, it's a lot to learn all at once, but I'm learning by working on an instrument that is going to go on the Lucy mission. And so we are testing the instrument right now before launch. And so then the next thing that I do is data analysis. So once we actually send the instrument to an asteroid or to Mars or to whatever planetary body, then we need someone to interpret the data that we get back. And so that is also what I do. And here you're seeing on this slide some pictures of rocks on Bennu. And we've determined that these rocks on Bennu are actually come from somewhere else. They're not native to Bennu itself. So that was kind of a fun finding from OSIRIS-REx. And then the last thing that I do, and I have a picture here of someone writing some squiggly letters. As a scientist, I think there's this idea that I'm in the lab or writing code or doing math full time. And I'd say about 50% of my job at the moment at NASA involves writing. So I'm writing proposals, I'm writing conference abstracts, I'm writing papers to be published to tell other scientists what we found. So I'd say if you're a really good communicator, you definitely should look into being a scientist because we need good communicators.
This might be a good time to stop and ask you some questions that we've been getting in the chat window, Hannah. The first one is, do you think Bennu is a gateway to the past in understanding the Big Bang?
Wow, that is quite a question. I'm very impressed. I think Bennu has shown us that it is definitely a gateway to understanding the past. The things we're trying to understand are not so far in the past as the Big Bang necessarily, but more so when our solar system formed. So not 13 billion years ago, just a measly 4 or 5 billion years ago. But it does. We think that Bennu was, or Bennu's, the body that Bennu came from was formed really early on in our solar system. And so Bennu itself records the conditions of that early solar system, which is partly why we're there. That's what we're going to look at. What was it like? What was the composition of the early solar system? These are the questions we're asking.
Yeah, so that actually kind of leads into the second question that we've gotten is, what do you think you will discover with the sample? And what type of materials do you expect the sample to be made of? So you've kind of led into that a little bit, but maybe we can dive into it a little bit more.
Yeah, so this gets at what is near and dear to my heart, because this is the work I've been doing for the mission, which is I'm looking from the spacecraft at the asteroid and trying to figure out what it's made of. And so we have some really exciting findings. We think that there are clay minerals on the surface that are hydrated, so they have OH in them, and they tell us that there was once water interacting with these rocks. So that's really cool. And we just a couple days ago published our results that we have organic materials on the surface. And so that was one of the goals of the mission, was to bring back a hydrated and carbon, so carbon in this case, we're thinking about organic carbon compounds, a carbon-rich sample. And so from our spacecraft observations, we're pretty sure that the sample will have these things. But we think the sample, when we actually measure it back on Earth, is going to tell us even more.
Okay, so the questions are flying in now that you've been talking more about that. So I'm going to jump around a little bit just to make it make a little more sense. But they want to know, why is it important to know about our past?
Yeah, so I mean, it might not be important to you personally, but hear me out. One of the things that we're trying to understand with asteroid Bennu is that we think asteroids like Bennu probably impacted the early Earth. And they carried with them these organic compounds and these hydrated minerals that I just mentioned. And they probably brought those things to Earth. And so we think that we might actually be able to understand some of the things that may have given rise to life. So I think if you're at all interested in like, why are we here? Are there other living things out there? Then you're kind of interested in these conditions of like what was happening and what could have given rise to life. So they're big, sometimes even philosophical questions, but those are the sorts of things that we're trying to get at.
That is so interesting. Let me see. So do you know which body Bennu came from? Like, do you know, is it from a larger planet, or do you know anything like that?
We know something about the body it came from. We don't think that we'll find that body necessarily, but we think that what happened is that there was a bigger asteroid. We think it was maybe 100 kilometers across, whereas Bennu's like half a kilometer across, so Bennu's much smaller. So we think that this big body existed somewhere in the main belt of the asteroids, and that it was hit and it broke up, probably into lots of small bodies, Bennu being one of them. Then at some point, Bennu makes its way from the asteroid belt, and it comes a little bit closer to Earth, which is where it is now.
Do you think life is possible on Bennu?
So we don't think that any life exists on Bennu. We think that possibly there were these conditions. For instance, there may have been water flowing through the asteroid that could have been, what we would call habitable conditions potentially. But we don't think that any life actually existed. There's no atmosphere. It exists in this really intense radiation environment. So in a few ways, it's not really, so nice in terms of life. So really, we're thinking about it in terms of delivering the components that you need for life more than life itself.
Okay, I understand. So back to OSIRIS-REx. Can you tell us how you'll be retrieving a sample and how that sample will be returned back to Earth?
Yeah, so this is the really fun part, and I'll say that it's happening on October 20th, so next Monday or Tuesday, but put it on your calendar. It's going to be really fun. We are going to try and grab our sample, which involves getting very close to the surface. And we have an arm on our spacecraft that is essentially going to touch the surface, and then it acts a little bit like a vacuum cleaner. It kind of takes some of the really small pieces of the surface and kind of sucks them into itself, which is then stowed into the spacecraft into a sample container. Then the whole spacecraft will leave Bennu and will come back. It will fly by Earth, but the whole spacecraft isn't going to come back to Earth. It's just going to drop this sample container, which is going to hit somewhere in New Mexico, we think. So at a military base in New Mexico. So it will hit the ground, and we'll go and we'll pick it up.
So you're going to run out there with a baseball glove and wait for it to come down and you can catch it, right?
I mean,
That'll be quite a
if you live
catch.
in New Mexico, you'll be fine.
That's great. A student wants to know when the next time Bennu will come by, if ever, again.
So yeah, Bennu was partly chosen because it's called a near-Earth asteroid, and it has an Earth-crossing orbit. So every so often, it comes a little bit closer to Earth. And that's partly what made it nice and accessible for our spacecraft. It's also part of why we chose Bennu because over 100 years from now, there's this really, really tiny percentage chance that Bennu could hit Earth. And so what we want to do is we want to understand things like, how is Bennu's orbit changing through time? What is Bennu made of? Is it really hard and if it hits something, it's gonna create a giant deadly crater, or is it gonna kind of break up in the atmosphere? And so again, the chance of it hitting Earth is even 100 plus years from now is less than 1%. It's very, very, very tiny. But part of the mission is understanding exactly these orbits and exactly the chance and exactly what might happen. So that was part of our goal.
So I think you brought a video with you today about the OSIRIS-REx mission. So do you mind sharing that with us? We can maybe see some more images and what the spacecraft actually looks like.
Yeah, so this video will give you a good view of what our sampling will look like on October 20th, which might help you visualize a little bit better what we're actually going to be doing.
Great, thanks, Hannah.
Over 200 million miles away from Earth, OSIRIS-REx is preparing for NASA's most ambitious sample return since the Apollo program. After months of detailed analysis of Bennu's terrain, the team selected the Nightingale crater as the sample site for the mission. OSIRIS-REx will need to carefully dodge rocky hazards as it descends to a space no larger than a few parking spots. The spacecraft has mapped the terrain in high resolution, capturing a stunning catalog of images across Bennu's rough surface. And now, we are ready to target Site Nightingale for the touch-and-go sampling event. OSIRIS-REx is prepared to begin its descent down to Bennu's surface and finally collect a sample. Using its database of images from Nightingale as a guide for its onboard navigation system, natural feature tracking, OSIRIS-REx will steer itself to the tag location, dodging Bennu's rocky hazards along the way. After years of preparation, analysis, and rehearsals, our target is in sight. OSIRIS-REx is ready to tag.
That is so awesome. So the TAG event is next Tuesday. And just so the students know, TAG is actually an acronym, right? Standing for touch and go. So next Tuesday, it's going to kind of pogo off of the surface of Bennu and grab that sample. So a student said it's basically like a giant space vacuum. I thought that was funny. Okay, so they're going to return the sample back to you. And then when are you expecting, did you say what year you're expecting that sample to return to Earth?
2023.
Okay, so we've got a little bit of a wait. I remember the launch, it was in 2016, and then you arrived in 2018, and then it's been orbiting Bennu ever since then. And I read that it's actually created a world record of the smallest planetary body that we've ever orbited and the closest that we've ever orbited. So congratulations on that record. Another question from the students. Do you think Bennu has a core with heat, or does it have its own gravity?
It probably doesn't have a core. It's very, very small. Most things with cores are bigger because you have to have some amount of melting. Typically, a core, when you, in the classic sense that you think of it, you would melt some of your rock and separate out some of the metal that would go into the interior. So Bennu is too small for that. We actually think, we call it a rubble pile asteroid. So we think that it's actually just, you can imagine a bunch of boulders all stacked together all the way down. And then, what was the second question? I'm sorry.
If it has gravity.
Oh yeah, so it does have gravity. Because it's so small, the gravity will also be relatively small. So if you were to go there, you probably wouldn't be able to walk around like you can on Earth. But one of the really cool things we found is that Bennu is actually spitting out particles, which we never thought we were going to see. But it's shooting off little rocks, and you can actually watch the rocks start to orbit Bennu. And some even will fall back onto the surface. And so you need gravity to have that happen. It is keeping some of these rocks, near it.
Well, it's interesting that you say that, because a student wants to know that if Bennu is in danger of colliding with Earth someday, is it possible that Earth captures it in its gravity field and it become another moon of Earth's?
That would be really cool. I'd be excited about that. Well, I say a number of things are possible. I think the probability of that is going to be very, very small. You have to be, at just the right position, approaching at just the right speed in order to be captured. Most things will not do that. So you're either going to be too far away, you won't interact with Earth's gravity really, and you'll just keep shooting by, or you're going to be a little too close and you are going to interact with Earth's gravity and you're going to get sucked in. Ending up in the kind of happy in between there, it would be, I think the chance of that is going to be near zero.
Can you compare Bennu's size to something that might be familiar to students? Like, how big is it?
Yeah, so there's a great image on the internet if you look up Bennu's size, in which it's compared to a number of things, one of which is like the Eiffel Tower, I believe. So it's not very big. It's half a kilometer, so you can imagine that you could probably run that in a couple minutes.
Oh, wow. That's interesting. So we've got just a couple more minutes left of our episode. So are you enjoying your life or your work at NASA right now? I know there's another slide that we can show what your work life is like.
So I have shown my current office setup. Like everyone else, I am working from home most of the time. So that is enjoyable in a number of ways. I have some nice office mates who keep me company. But it is really fun to be able to go into work and be able to interact with colleagues. And I am missing that a lot. I do get to go in sometimes because we are testing our instrument right now. And you can see what a test chamber looks like in that other image. So you can see what I do for part of my time there. But yeah, I am enjoying my life at NASA, certainly.
So I would definitely encourage students to apply for internships and come out and work for NASA, because there are plenty of careers and a variety of things that you can do, like being a scientist at NASA like you, right? Yeah.
Yeah. It's a great place to work.
So I want to take this time to invite students on a mission of their own, similar to what the OSIRIS-REx is going to be doing next week. I want to challenge you to build a device that can take a core sample from a potato asteroid. So to find this activity, we're going to drop that link into the chat box, and I encourage you to build a core device and share your sampler with us on your social media, hashtag NextGenSTEM. And you can also tag at Osiris Rex on Twitter or hashtag return, back to Bennu? I can't remember. We'll put those hashtags in the chat. Thank you. I knew it was similar to that. I like that. So to Bennu and back, hashtag to Bennu and back. Next week is our next episode on Monday, the day before that tag event, with a photographer that works with the James Webb Space Telescope, Chris Gunn, at 1 o'clock Eastern on Monday. So I encourage you all to hit that subscribe button down at the bottom so you can follow us on the YouTube channel and watch more of our NASA STEM Stars episodes. So thanks again, Hannah, for joining us today. I hope you had as much fun as us. And that will conclude this episode, and we'll see you next time, STEM Stars.
A new era of exploration is beginning. NASA is building on its experience in low Earth orbit and preparing to go farther, setting up a base camp in orbit around the Moon, known as the Gateway, exploring the surface of the Moon like never before, and preparing to one day go to Mars. To accomplish all this, NASA will need a new spacesuit for its astronauts, one that's more flexible, versatile, and durable than any made before. Engineers are now hard at work designing, building, and testing the new suit, making sure it's up to the task for future exploration. Some of the greatest moments in exploration have taken place with a human in a spacesuit. Whether it was a first journey outside the spacecraft or traversing mountainous moonscapes, the spacesuit made it possible. The act of sending a suited human outside the spacecraft is called EVA.
What is an EVA? EVA is an acronym that stands for extravehicular activity, which is what most people know as a spacewalk. It's whenever we take astronauts and we let them go outside to do useful work in the vacuum of space.
The spacesuits currently in use for NASA EVAs were designed in the 1970s for space shuttle missions. They have been upgraded over the years for work on the International Space Station and have served NASA well.
In the past 20 years, there are a handful of types of spacewalks that we've done. We've done planned spacewalks for maintenance. As hardware breaks, we can do contingency spacewalks. As technology improves, we can upgrade hardware. Or like with the Hubble Space Telescope, we're actually repairing very sensitive scientific experiments in order to enable science.
Those EVAs took place in microgravity, where astronauts float and need to use their hands to move from place to place. But moonwalkers, working at 1/6 Earth's gravity, will need spacesuits that let them use their hands and feet, walking to destinations and bending and reaching as they explore. For this new type of work, NASA has been testing prototype planetary suits, culminating in a new suit design, the XEMU.
The XEMU is Exploration Extravehicular Activity Mobility Unit. So it's an exploration spacesuit. So it's a spacesuit that you're going to use as we move forward on Gateway missions and on the lunar missions with Artemis. And then we're using all that to test the suits you would want to use to go to Mars in. So eventually you're going to have to be very independent and very confident in your hardware when you go and do a mission that far away from Earth.
One of the most obvious changes in the new spacesuit is the way astronauts get in and out of it. Donning the current suit is a multi-step process of wriggling into the upper torso and then getting help attaching a pair of space pants. The new generation spacesuit features a hatchback, where astronauts simply slide in and out of the one-piece body of the suit.
Wow, it feels much better.
Another big feature of the suit is the way the astronauts are able to move while wearing it. Apollo astronauts learned they had to hop to get around on the moon. The suit design sometimes made it difficult for the astronauts to work.
Up. Okay. We see that one went all the way in. Not quite. Like that.
Engineers learned valuable lessons from those Apollo suits. The improved design for the next generation spacesuit will allow astronauts to walk on the moon, not hop. Additionally, astronauts will experience an improved range of motion.
The new suits, the planetary walking suits we're working on now, we really hope to provide improved mobility and comfort along with reduced injury potential. And really, like I said, provide the best tool to the crew member that we can provide. Then we want to be able to provide them the ability to kneel down and pick up a rock, like they're going to want to do in their geology science that they're working on. We want this to be a very reliable and durable suit so they can use it day after day in a dusty environment and not have to do a lot of maintenance with it while they're needing to do their mission. So there's a lot of those kinds of aspects that go into improving the suit that we're going to provide for the lunar missions.
Improved mobility is not the only feature engineers have been working on. The astronauts will also be carrying a special backpack known as the PLIS.
So the PLIS is the Portable Life Support System. It's the backpack on the spacesuit, and it has all of the interesting parts to keep the crew member alive while they're on their spacewalk. So it has oxygen stored as pressurized gas for breathing, pressure regulators that regulate the oxygen pressure inside the spacesuit, and then a ventilation loop and a water loop that we call the thermal loop that provide trace contaminant and carbon dioxide removal from the breathing environment, and also cooling for the crew member and the suit onboard avionics and electronic systems.
While the PLIS has been on previous spacesuits, this improved version will offer new technology, greater control of its systems for the astronaut, and longer life for each EVA, allowing more exploration.
The PLIS labs are awesome, super fun places, and we physically assemble the parts to build the life support system, and then we test it. It's our opportunity to find things and fix things before we get it on orbit. We love what we do. We really want to see this system fly and be useful and help a person explore the moon in a more capable manner than they were able to do during Apollo. So it's a great job.
So I want you to perform some isolated joint movement to understand how the suit moves and then be out.
Testing for the new spacesuit continues underwater in the Neutral Buoyancy Lab. Here, the weightless environment of space can be simulated to put the suit through its paces.
So being able to test the suit in the pool and microgravity environments allows us to iterate on our design and make it better and get feedback from astronauts and from other instructors and trainers.
Could you reach all the way across and do the cross switches with your opposite arm?
Oh yeah, it's really easy to get all the switches with my opposite arm. I would rate this as excellent.
Come on. I know, I guess it's gonna get lower and flatter.
Yeah.
Hold on. Oh my God.
You did it! Very good.
So if this could happen in real life, this is a spectacular translation.
Rex and I are very lucky. It is like a brand new spacecraft.
Even has the new smell and everything.
It does. New car smell.
Spacesuits are also tested in the Active Response Gravity Offload System, or ARGOS.
Yeah, so the ARGOS electronically is able to tune an astronaut exactly to whatever gravity it is that we're practicing that day, whether that's microgravity, lunar gravity, or Martian gravity. The other nice thing about ARGOS is you're able to get the instructors and the engineers right next to the astronauts as they're working, helping the astronaut figure out a problem as they work through the development of that test for the suit or for a piece of hardware and get that real-time feedback.
Spacesuit hardware is not the only thing being tested on Earth. NASA is looking at human performance as an important factor in designing EVAs and spacesuits.
So related to a spacesuit, a lot of times people think about the actual engineering, the hardware, the different pieces, but I want to look at the EVA scenario from the human really inside the suit and make sure that their performance, both physically, cognitively, is going well. So we want to look at things like physical exertion, cognitive workload, injury risk, and really just trying to make sure that they're not impaired by the EVA system any more than they have to be.
The NASA team uses virtual reality technology, motion capture, and other tools to study what it takes for a human to conduct an EVA.
And what we're able to do is bring actual, no-kidding data to the table that really removes the opinions. That's probably our primary benefit for how we kind of enhance the EVA community is we take a look at this not from a hardware, not from an operations standpoint first. We look first at the human and then kind of say, what do they need to be able to do to be ready for the job?
All the work on the spacesuit here on Earth is building up to the ultimate test, to fly it in space.
So we're actually building a flight unit of that XEMU, and we're going to launch it to the International Space Station. And we will do an EVA with a current spacesuit, an EMU that we use today, and the XEMU with it. We'll go out in pairs, and we'll have the astronauts working together, one in the old suit and one in the new suit, and we'll test its functionality in a microgravity or a low-gravity environment out in the vacuum of space. That will help us test a lot of its systems.
The EVA on the space station will set the stage for the future, when the suit will need to perform a variety of missions beyond low Earth orbit.
Yeah, so a great example is NASA's Gateway. So even though it is in lunar orbit, it's still a microgravity platform, so astronauts would still be floating in space. And so we can use a lot of the lessons we learned from the International Space Station to do spacewalks on the Gateway. It's actually really advantageous to use one spacesuit both at Gateway and on the lunar surface. So the exploration spacesuit can do both of those things.
For EVAs on the moon, the new spacesuit will give astronauts unprecedented abilities as they explore the lunar surface.
Really, this is the first time we're trying to bring a suit that's optimized for human performance and optimized for lunar exploration so that you can actually bend down, interact with the ground, so that you're going to have the visibility that you need, the mobility that you need to accomplish these tasks.
This new suit will allow us the flexibility to really do exploration. Get down on the surface and send geologists to the surface and really let them act like geologists in a spacesuit. This is the first time in history that a suit like that will have been created, and it's really exciting to be part of that. To do what NASA was meant to do, and that is to do exploration. And this suit will really help enable the agency go do exploration.
Well, everyone in my generation wasn't alive the first time we went to the moon, and we want to do it again, and we want to do it better. We want to go do more science, we want to stay longer, we want to get more out of it, and we have the technology to do it now. So we're really excited about it.
With its new technology, new design, greater mobility, and greater versatility in how it can be used, NASA's new spacewalking suit is truly tailored for the next generation of space explorers.
When we are called to do an experiment, sometimes it's a very short lead time. We get a 12-hour call, and we're in.
My advisor and I, we have to work together. He's talking to the astronauts, I'm talking to the cadre, and so it's really difficult to take it all in.
Very nice. Very good. Try not to break them up, but that's a very good disturbance. And now back and forth the opposite direction.
What's funny is I forget who I'm talking to sometimes. I'll have conversations where it's like, oh yeah, you know, we had an experiment yesterday. It was on the space station. We were talking to the astronaut, Doug, and it's so casual. And it's like, most people are like, what do you do?
Throughout this season of NASA Explorers, you've seen what it takes to send science to space through the eyes of one team of researchers. But they aren't the only ones. For 2 decades, the International Space Station has hosted science from thousands of researchers across the globe.
The importance of the ISS to the research community is huge. From the very basic
phenomenon of taking gravity out of the equation is that the ISS is really the only platform we have right now that gives you access, long-term access, to a microgravity environment.
You can do the experiments, on Earth, but those are almost a precursor to, okay, now let's remove gravity and see what happens. Does it change?
If you're like me, you're a scientist who's trying to, unravel the mysteries of science, and someone shows you a shiny new tool, which is microgravity, which can, make science different. And different is what we constantly shoot for.
And different can take time. Before new scientific discoveries could be made, we had to transform an orbital outpost into an orbiting laboratory.
In the early days, it was so focused on building, constructing station and making things safe. And then we started stepping up the number of hours a week that we can use crew time for experiments and research.
That was a very exciting time. The space station would have more capabilities for science. They would have more equipment up there. They would have, freezers, glove boxes, microscopes, etc. Things that we could use to extend the scope of our science.
Space station became a laboratory. It lent itself very well to this concept of fly an experiment, you get the results back, just like you would be in your own laboratory at home. You get more questions as well as answers.
And during that time, a lot was learned. A lot of surprising things were learned. And with that knowledge now, we're developing experiments that are much more advanced in terms of their engineering application.
It's been an extraordinary journey to watch over the past 20-odd years how this has all kind of come together and become, I wouldn't say routine, but accessible. And that's a really powerful thing.
The same thing that gives us new insights also creates unique challenges. Microgravity changes the way everything works, including science.
Working in space, as you can imagine, has a lot of challenges. Everything has to be compact. If you're gonna send something into space, it has to be small. And how can you fit an entire lab bench worth of science into something, your size of your hand? And yet, we still get great information. We still, are discovering things, all the time, and I think it's incredible.
Up till the NASA twin study, I was an Earth investigator. The biggest adaptation that I had to make was, on Earth, there's an ample supply of all the tissue that you need, whether you need blood or you need urine. So we had to work together and figure out a plan on how to use 1 vial of blood instead of 10 vials of blood. The stress of these precious, this is the most precious samples I've ever worked with, was kind of novel.
There were different students that all got together to create this project. It was really stressing on every review because, of course, you're they're gonna say everything's wrong and they're gonna blame it on me or whatever. We knew that it would be difficult, but everybody that jumped into the project pulled through. And at the end, we achieved a successful mission. So I think that's awesome.
What we've learned from more than 3,000 space station experiments is helping us back here on Earth and on our quest farther into space, to the Moon and Mars. These experiments are aiding drug development to fight diseases like Alzheimer's and Parkinson's. We've learned about combating bone and muscle loss, which could assist people suffering from osteoporosis. We've tested how to grow plants in microgravity, a critical component for feeding future space explorers. None of this would have been possible without the astronauts, the humans living and working aboard the International Space Station.
Having the astronauts there to help us was a critical part of being able to do more complicated science, to get higher science yield out of the science that you were doing. They were incredible as people who were there to troubleshoot your experiment should you need anything.
You can never replace a set of human hands. I don't care if it's on station, on the moon, on Mars. There's just something that people can adaptively do that you'll never get a machine to do.
You can collect a lot of data with robotic sensors, but there is still a very big role for humans to play in being able to make on-the-fly decisions.
Okay, that has a little bit of a bubble on the end. Do you want me to force that out?
If it's possible, if you think you can do it with the tip, yeah, we would appreciate that. At this point forward, this is our DNA to sequence, so the most we can retain, the better.
It was rewarding to be able to put my hands on and know that we're doing productive work. Sometimes we get thrown a curveball and something goes wrong.
Station Huntsville on 2 for TJ and ABRS.
So now they go, all right, we got to get you to go into the guts of this thing, go find these 2 wires. Have you ever seen those scary movies where the bomb diffuser says, whatever you do, don't cut the red wire? That's kind of what it feels like. You've got somebody who's spent their life developing the research that you're working on, and you're about to go into the guts of his experiment, trusting you very well to do the right thing and not cut the wrong wire. But that's the kind of stuff we need to do when we start going farther and farther away, when we start encountering anomalies we didn't think were likely. And so the crew has to be able to be adaptable to be able to do that. And that was really exciting and fun to be able to accomplish.
TJ, we copy that, and who would have thought a blown fuse would make so many people so happy?
Jeff happened to be orbiting and looked outside the window and saw this eruption just happening. And then he said, hey, I wonder if anybody knows this volcano is erupting. And so he actually called the USGS and said, hey, I see a volcano erupting. Do you guys know about it? First, he had to convince them that he was actually who he was and was actually calling them from the space station. But once you get past that, they then confirmed with other data, like, well, you're right, it is erupting.
So I think those are some of the ways in which the astronauts just play an incredibly valuable role when they're up there helping us with the experiments that we do.
These past 2 decades of microgravity science, they're just the beginning, the start of humanity's continuous presence in space. And the impact of the research in this novel environment is already being felt around the world.
I think most people would not realize how impacted their life is by space. There's a finite number of experiments, but that is a finite number of experiments in a very, very smart community that's very good at sharing the results. There is a real sense of the betterment of humanity in space. You know, it's one place we can all really collaborate and all really get along.
I think it's safe to say that microgravity has allowed writing several new textbooks.
And the more we have more and more scientists working in different arenas to help inform this science, I think the better it will be for the safety and health of the astronauts and the people that follow. We are just at the tip of the iceberg. We have a lot more information that we're going to find out, a lot more information that we're going to need to find out in order to get us prepared for long-term exploration, as we humans are always excited to do.
Space Station now is acting like a test bed, a proving ground for new development, new system hardware, as well as how we're going to be doing research and what kind of research we want to be able to do in a near environment, 240 miles above the surface, versus seriously long distance away where there's time delays up to half an hour-ish that we need to be practicing for, and now's the time to be able to do that.
I would say before I started working at the lab, it was kind of an abstract idea, and there was always the joke about, oh yeah, humans will go to Mars, and it didn't really feel real. And now it feels real, and what's incredible is, I will have a piece of that.
I like to think that some of the work that is being done on the space station lays the foundation for us to be successful on another planetary surface. Will I ever get there? No, it's not likely. But I do hope that someday that somebody thinks back on, wow, it's really great that we learned about X, Y, and Z things from the Paul and Ferrell research, because we'd never be successful on Mars without it.
We'll learn more and more the farther and farther we go. The first stepping stone, though, is the proving ground that we're calling the International Space Station.
Hey, NASA astronaut Reed Wiseman.
Hey.
Do you think you have a few minutes to answer everything about living in space?
I got all the time in the world.
Awesome. Well, where are we?
We are in the Space Vehicle Mock-Up Facility. It's a gigantic building at the Johnson Space Center in Houston, Texas. And this is where astronauts spend the bulk of their time training for spaceflight.
Is this the window where you took all of those really cool pictures of Earth?
This is the cupola. It's a series of 7 windows that look down on the Earth.
Nice. How big is the International Space Station?
They say it's about the size of a 5-bedroom house. It's kind of hard for me to conceptualize. In reality, it's just really narrow and really long.
How long did you have to train before going to the ISS?
About 5 years.
And how many total days have you spent in space?
165.
What's the record?
Jeff Williams, he has the US record, 534 days in space. But Russian cosmonaut Gennady Padalka, almost 1,000.
Wow. What's a groundbreaking experiment that you completed aboard the ISS?
I survived.
I heard you age faster in space.
Maybe a little bit.
Is there a maximum height or age that you have to be to become an astronaut?
We used to have restrictions on that, but now it's pretty much come one, come all.
Is there Wi-Fi?
There is, but it's not as good as it is on Earth.
How do you get in contact with people on the ground?
We have space-to-ground communication systems. It's basically a radio or a walkie-talkie, and we just call on this and say hi to Houston.
Is there a delay?
Almost none.
How did you get to the station?
A rocket.
How long did it take for you to get from Earth to the space station?
Takes about 6 hours.
And how long did it take for you to get back?
Oh, that's a crazy ride. It's about 3 hours long.
Any jet lag?
Horrible jet lag.
How often do you get to talk to your family?
Get to talk to them once a week.
Ever prank call anyone?
Of course you prank call people.
Ever get homesick?
Yeah, you get homesick a little bit.
So are the beds comfy?
There are no beds.
I heard you have to be strapped to a wall.
You do?
Are you claustrophobic?
A little bit.
What else can you do in your room besides sleep?
You can read, watch TV, do some work, whatever you want.
Do you have a bedtime?
Everybody has a bedtime.
Do you have alarm clocks?
I use my watch.
How many crew members do you have?
It was me and 5 others.
Were there any language barriers?
Doc and Yeshna, of course there were language barriers.
Ever get sick of your roommates?
No, you never get sick of your roommates.
What did you do in your free time?
Oh, you look out the window.
What's a typical breakfast aboard the space station?
It was very much like a breakfast on Earth, so I liked eggs, occasional oatmeal, maybe even a waffle.
Was the food any good?
I actually thought the food was pretty good.
What's your favorite meal on the station?
I love chocolate pudding cake.
How do you cook your food?
You can either inject it with hot water or put it in a food warmer.
What's the first thing that you ate when you got back to Earth?
I really wanted a pizza, but I saw a salad and went for it.
So did you have to work out?
You work out twice a day for about 2.5 hours, 2.5 hours.
And what kinds of exercises?
Primarily, you're either lifting weights or running on the treadmill. Our treadmill is attached to the wall, and so when you're on it, you're running straight down towards Earth. Very weird feeling.
So how do you stay on the treadmill without floating away?
Bungee cords.
So do you burn the same amount of calories as you do on Earth?
I think you burn a little bit more because your brain is always active.
I heard that in microgravity, sweat sticks to you.
It does. If you have hair, it kind of builds up in your hair and you get this big sweat bubble on your head.
How do you shower?
We have soap impregnated towels.
How do you pee in space?
Ooh. We have a funnel.
Where does your pee go after you flush?
A little bit of processing and then right back into the drinking water.
How do you pee in a spacesuit?
We have a diaper.
How much water do you have to drink each day?
You drink just about the same that you would on Earth.
Do you ever run out of anything?
Free time.
How do you get more supplies?
We have cargo ships. We have great companies like SpaceX, Orbital. We have Russian resupply vehicles and also Japanese HTV spacecraft.
What'd you miss most on Earth?
Oh, my wife and kids.
What personal items did you take with you?
Photos of my wife and kids.
Did you bring any space souvenirs home?
You always have to bring souvenirs home for your kids.
So I have to ask, what's your favorite planet?
Oh, it used to be Saturn until I saw Earth from space.
And if you were to travel anywhere in the solar system, where would you go?
I work at NASA. We all want to go to Mars.
Does the space station ever get too hot or too cold?
Oh, we keep it a balmy 72 all year round.
Nice. How about the temperature of space?
Plus 200 F to minus 200 F.
What about the temperature inside the spacesuit?
It's actually pretty warm, pretty nice, pretty comfortable because there's many layers of thermal protection.
How much does the spacesuit weigh?
Oh, it's really heavy. I think it's about 300 pounds.
How do you do your laundry?
We throw it out.
Do you have to clean the spacesuits?
Of course you got to clean the spacesuits, especially after a spacewalk.
How long does it take for you to put on a spacesuit?
About 45 minutes.
Can you put it on by yourself?
If you're in a pinch, you can put it on by yourself.
How long does a spacewalk normally take?
We train for about 6.5 hours.
And what's the max amount of time a spacewalk can last?
The maximum is about 9 hours. I think 8 hours and 54 minutes is our record.
How's the view?
Awesome.
What's the hardest thing about a spacewalk?
Just knowing that you're outside, and if you mess anything up, you've destroyed a $100 billion spacecraft.
And what's the most rewarding?
Coming back.
Sounds awesome. Well, I'm sure there are a lot more questions, but I know you're busy, so we'll save those for another time.
Sounds good.
Awesome, thanks. Have a good one.
See ya.
Hello and welcome to another episode of NASA Science Live. I'm your host, Lauren Ward. Sea levels across the globe are rising as a result of a changing climate, and the rates at which they are rising are accelerating. For nearly 30 years, NASA has continually been tracking the global surface height of the ocean from space in order to understand sea level rise. Rising sea level affects everyone across the globe, from coastal communities to those living in landlocked regions. Today we will dive deep and discuss how NASA and others across the globe are monitoring our oceans and what communities are doing to alleviate the impacts of sea level rise. But first, what exactly is sea level rise?
Around the globe, sea levels are rising. Greenhouse gas emissions cause our planet to warm, and Earth's oceans absorb about 90% of the excess heat. As ice melts at the poles and high in the mountains, and the molecules of ocean water expand, the seas are making their way onto land. Since 1880, sea levels have risen about 8 to 9 inches. But the seas don't rise uniformly. Some places are at higher risk for flooding, and sea levels are rising faster as time passes. Right now, sea level is rising about 3.3 millimeters a year, 30% faster than in 1992. Here at NASA, we're using satellites, like the new Sentinel-6 Michael Freilich, along with ships and airplanes, to study the processes driving sea level rise and the effects of rising seas.
Over the course of nearly 3 decades, a series of satellites have circled our planet continuously measuring sea levels. Their data have helped researchers reveal mysteries of weather phenomenon like El Niño, and have also helped researchers forecast how much sea level rise could impact our coastlines. Now, engineers and scientists are preparing to launch 2 identical satellites to add to this legacy. First, Sentinel-6 Michael Freilich, and second, Sentinel-6B launching 5 years later. Here to tell us more is the Sentinel-6 project manager, Parag Vazay, who has been part of sea level rise observations for nearly 30 years.
I see pictures of coastal inundation and flooding. What might happen in the next 100 years with the 200 million plus people who live in those low-lying coastal areas all across the globe. My name is Parag Vazay, and I do anything and everything that's needed to make Sentinel-6 project successful. Sentinel-6 is all about water.
So this is a 1/3 scale model of the Sentinel-6 satellite.
Sentinel-6 is a collaboration with NASA, NOAA, the European Space Agency, and also EUMETSAT in Europe to measure sea level.
This sort of top half of the satellite houses the main instruments.
The history behind this goes back 30 years. I've worked on Topex Poseidon, JASON-1, JASON-2, JASON-3, and now Sentinel-6. All of them are the same series of missions. It's a great feeling of satisfaction. I had aspirations right from childhood to somehow work in the space industry. I knew that I wanted to work in something that made a difference. This is the room where we developed, integrated, tested the Sentinel-6 instruments, and then right here is where we packed it up also before we shipped it to Germany. Seeing that come to fruition is a personal satisfaction and an emotional satisfaction. The importance of this project and where it touches is on all walks of life all across the world.
Parag, thank you so much for joining us.
Thank you for having me.
All right, let's kick this off. Why is it important to study sea level rise at all?
Yeah, sea level rise is an extremely important topic for everyone. something that people have seen in their backyards with the oceans actually changing over time. It's something that people are noticing more recently, but something that people have known for a long, long time. And it affects everyday life. It affects commerce. It affects shipping, all kinds of applications where people really want and need to know what's happening on our oceans, which surround our Earth for the vast majority of the Earth having oceans, 70%.
You make a great point. It's most of planet Earth. So what will this mission in particular contribute to the effort of studying sea level rise?
Right. So sea level rise or sea level has been an important topic for people, but really understanding and quantifying what's happening with the ocean is difficult to do. It's changing slowly, but it is changing, and understanding how quickly that's changing. It requires really a measurement, a very precise measurement, and a continuous measurement. So Sentinel-6 will continue that measurement that's been established for 28 years. And what's special is really continue that over the course of the next decades with 2 satellites, not just a one-off satellite, but 2 satellites to really establish and continue that.
That's remarkable. One thing that I think is really interesting is how will it actually measure sea level rise, and how will that contribute to what we already know about sea level rise?
Yeah, so people have been interested in measuring sea level. They've been using, dipsticks essentially in the years since when ships were out on the ocean, and people were curious what's happening in living close to the ocean. But that is a difficult process to really understand what's actually happening precisely across the world. So satellite remote sensing really is a solution that allows us to understand what's happening precisely over all of the oceans across the whole world.
So I understand Sentinel-6 is an international mission, speaking of seeing the whole world. Can you speak about some of the global collaboration that happened to get this mission off the ground?
Yeah, so it's a global problem. It's a difficult problem. So it requires a global solution, and that means people from all skill mixes contributing to that. That has actually been happening with engineers, scientists, users for many, many years. But Sentinel-6 brings that together in an operational sense. It goes from taking something that's been done together and bringing all the resources and minds together traditionally for the past 28 years, and really looks towards making that into an operational service that's going to continue for the next decades or more.
Yes, as you say, global problems require global solutions, and we are doing just that. But that's all the time we have. Thank you so much for joining us, Parag.
Thank you for having me.
A satellite dedicated to uncovering new knowledge about our rising seas deserves to be named after someone who dedicated his life to understanding our oceans. That is why NASA's European partners on this mission named Sentinel-6A satellite in honor of Michael Freilich, a world-renowned oceanographer and former director of NASA's Earth Science Division. Mike's contributions to Earth science were invaluable.
My story is likely quite atypical. I knew in 10th grade that I wanted to be a nearshore oceanographer. What has driven me is understanding how nature works.
And that's why humanity, not one agency, not one country, not one continent, but why humanity has been monitoring global sea level from space with exquisite accuracy for more than 28 years.
It's a world-renowned ocean scientist who, after a successful career in academia, came to NASA, and for 12 years, Dr. Mike Freilich led all of Earth science.
And he's really brought NASA back on the international stage.
And this is not all. You also change the discipline of earth science in a profound way, combining science and technology to understand our beautiful planet.
Mike Freilich's legacy is being able to build the coalitions that are necessary for us to get as much understanding of our planet as possible. There is not another person more deserving of this honor than Mike Freilich.
I'm very pleased to rename Sentinel 6A in the future to be called Sentinel 6 Michael Freilich.
You know, when I first found out that Mike had cancer, I want him to know that all the work he's done is extremely meaningful.
I am much better because of what I learned from him and because I had the opportunity to work with him.
Mike is a leader to all of us and a mentor and a person who has really advanced earth science for the entire world.
He was absolutely committed to dispassionately following the science.
He had high standards for himself and everyone around him.
We're able to raise the bar of what we can expect from ourselves, from our partners, and from our larger global community.
Mike had a very big, very full red pen. Everybody was always afraid of that red pen.
His pretty intense energy. One of the characteristics was the bouncing knee, which you never missed, and it was always there, and you could kind of gauge the way the meeting was going by the pace of the bounce.
I have a lot of hilarious emails on my smartphone exchanged with Mike, which I keep as a treasure.
It is a no-brainer that we all came together and that they were able to really rally around and allow the renaming of Sentinel 6A after Mike.
Earth system science is bigger than any particular agency. It's bigger than any single nation. It's bigger than any single continent. And I surely hope, because humanity requires it, that we make some significant progress in understanding.
You did good, Dr. Freilich, for all of us, and for that we're all very grateful.
Mike Freilich was a leader in earth science who believed in fostering international partnerships to improve our understanding of all Earth systems, including our oceans. Let's get to know some of the people behind this truly international mission.
This is this big, complex machine that we're trying to understand.
We really need to understand how it's changing. How is it evolving?
Wherever you live on this globe, the oceans will influence you in some form or the other.
We are answering those really interesting and hard questions that we all have about our universe and our planet.
My name is Séverine Fournier, and I'm observing our changing oceans from space.
I'm Shannon Statham, and here at NASA JPL, I help prepare Sentinel-6 for its journey to space.
My name is Shailen Desai.
My name is Parag Vaze.
My name is Ben Hamilton, and I'm studying sea level rise from space.
We're looking at a 1/3 replica of the Sentinel-6 Michael Freilich satellite.
Sentinel-6 is all about water.
This sort of top half of the satellite houses the main instruments.
We have the altimeter, we have the radiometer.
Sentinel-6 is a collaboration with NASA, NOAA, the European Space Agency, and also EUMETSAT in Europe to measure sea level.
And it's specifically capturing the height of the ocean.
The satellite is actually emitting a signal.
And that signal is bouncing back.
It measures the time it takes for that pulse to get back.
So we've been measuring the height of the ocean since the beginning of the 90s.
I've worked on Topex Poseidon, JASON 1, JASON 2, JASON 3.
We really need that long duration observation.
And Sentinel-6 is going to allow us to continue that record.
So that we can better predict what is the rate of change, what is it going to look like in a year, 5 years, 10 years from now, and so forth.
It's not just scientific curiosity, it really impacts the daily lives of people and their ability to plan for their future.
I see pictures of coastal inundation and flooding.
You start to realize the importance of understanding what sea level is doing now. We can use that understanding to know what sea level might be doing in the future.
Seeing that come to fruition is a personal satisfaction and an emotional satisfaction.
Scientists around the world are using this data to help people.
The importance of this project and where it touches is on all walks of life all across the world.
From space, it's just one planet.
Sea level rise is a direct result of climate change. As ocean temperatures increase, our global ocean expands. As ice sheets and glaciers melt, they add more water. But climate change has many impacts beyond sea level rise. We're joined by Dr. Ivana Cetinich, an oceanographer at the Ocean Ecology Lab at NASA's Goddard Space Flight Center. Thank you for joining us, Ivana.
I'm happy to be here, Lauren.
Always happy to have you. So we know that sea level rise is increasing the height of the world's ocean, but can you tell us about some of the other things that are happening due to climate change?
For sure. So ocean and climate are very interlinked. Ocean is part of the four systems of Earth, and each of them kind of have like a little thing that they're doing, and they're very interlinked through the exchange of water, carbon, or energy. And so if one kind of fails, the other one comes to help. And ocean's helping a lot and trying to control the climate change. But there's different aspects of different processes that are happening in the ocean that we can see as a result of climate change. First one is the increase of temperature, both in the sea surface and internal portion of the ocean all around the world. Then we have disappearance of the sea ice, mostly happening in Arctic region. Then we have the sea level rise that is impacted by these two processes that I mentioned before, that is seen all around the coasts, all over the ocean. And ultimately we have ocean acidification, which is a process that's happening because the carbon dioxide from the atmosphere is melting in the ocean, it's changing the acidity of the ocean. And all these things together, in a sense, are impacting the way that the physics, biology, chemistry, and geology of the work of the ocean is working, and then ultimately it impacts us.
So what I'm hearing from you is that it's a very complicated system.
Yeah, and very intricately connected.
Wow, yes. So I think one thing that people might find surprising is that, NASA has a suite of tools that it uses to study the ocean, and it's not just satellites. Can you tell us about some of those tools that we use to monitor the ocean ecosystems?
For sure. So as an oceanographer working at NASA, I always get like, what?
Yes.
But NASA does study Earth, and NASA does study oceans. So first we have satellites, and there's this whole fleet of NASA Earth observing satellites, and some of them are actually looking specifically at the ocean and give us this continuous synoptic view of the ocean's behavior in a sense. It talks about physics, the temperature, or biology. And biology is really cool because it looks at these teeny tiny phytoplankton, which are like teeny tiny plant-like organisms in the ocean. And I'm working on one of these missions that's going to be launched in a couple of years. It's called PACE, which stands for Plankton Aerosol Clad Ocean Ecosystem, and that one, among other things, will look at the diversity of that phytoplankton, these teeny tiny creatures. So you have the satellite, and then we go on field. We use aircrafts, we use research vessels, we use moorings, robots, field stations to kind of focus on specific questions, specific areas, and then ultimately we take all the data and plug it into the models. Such as big Earth system models that can really allow us to understand this interaction between the ocean and climate, ocean ecosystems and climate, and then actually predict what's going to happen with the ocean ecosystems of tomorrow.
Wow, that's amazing. I love that vision of seeing, planes in the sky, satellites, like, boats on the water, everything.
Yeah,
you got the whole suite.
Exactly. Yeah, it's pretty awesome.
It's amazing. I want to dig into that a little bit deeper. What changes are we seeing to ocean ecosystems due to climate change? This sounds like it's something that's kind of in your wheelhouse.
Yes. So, when you mentioned sea level rise, and that's the first thing that people think about, changing oceans, and that's felt along the coast. Like 40% of the people in the U.S. live along the coast, and that's where you feel it the most. But ocean has ecosystems, and all these ecosystems, although hidden from our eyes, they're there, they're present, and they're changing. So thanks to the NASA Earth observing satellites, we can see these changes. For example, there's these portions of the Earth that we call oceanic deserts, where the number of these phytoplankton are really low, and they're actually extending over the last decade or so. So we know that. Then we go back to the field and we use vessels, and we see that the types of phytoplankton in these ecosystems are changing. Some of them are actually moving polewards, kind of like towards, let's say, north. And so now, how does it affect you? I'm like, you live on the coast, you don't care about open ocean. Well, that phytoplankton is food for something. It's actually food for everything in the ocean. It's food for the fish. They will ultimately end on your plate. So these changes in the ecosystem, although you're not on a coastal area, will eventually affect everybody on Earth.
Yeah, everything's got to eat, right? That's
exactly.
That's kind of a hard and fast rule. So what strikes me, Ivana, is that a lot of this news is kind of discouraging. You work with data that is can be very dark. What do you do? Why do you continue doing this work, when the news that you're getting constantly is unhappy often?
Yeah. So, you get lots of data when you're working in NASA, and you're surrounded with amazing scientists who know much more than I do. And all that stuff is discouraging, definitely. But there's two reasons why I keep on doing it. First, this is our home. This is the only home we have. There's no other planet that we know of that contains life or on which we can live. Exactly. And the second thing, I do have a teeny tiny bit of hope in humanity that will change its ways and, kind of like probably, hopefully, change the path that we're currently taking in regards to the climate change.
I think we all are holding on to that spark of hope, and that's why we do what we do. But thank you so much for joining us, Ivana. We loved having you.
I'm super happy to be here.
Real-world impacts of our rising oceans can be seen in coastal communities like the Hampton Roads region in Southeast Virginia. Let's take a look to see how sea level rise is directly affecting their community and how they are using NASA data to help forecast future impacts.
Sea level rise is a measurable difference in water level over time, and directly contributing to that is, of course, climate change. So as the temperatures rise, polar ice caps melt, and slowly the water level rises all throughout the globe. And there are localized impacts of sea level rise.
In Hampton Roads, we are particularly vulnerable to coastal flooding.
The Hampton Roads region of Virginia is the second most heavily impacted region in the United States when we talk about sea level rise, after, of course, New Orleans.
We're standing here at the Hague part of Norfolk, Virginia, which is in the mouth of the Chesapeake Bay in southeast Virginia. This area will see what we call blue sky flooding quite regularly, where there's no storm event. And so this water comes up over onto this side, water breaches the bulkhead, floods the area around it and the road behind me as well.
A lot of my research, the Virginia Institute of Marine Science, involves the development of physics-based hydrodynamic models. These models tell us where flooding is going to happen before it does, when, and for how long. But you'll see all these individual structures here, most of them near the waterfront, are inundated. The information provided by NASA satellites mostly allows us to validate the accuracy of our model in terms of telling us where the flooding actually happened in space.
The maps that come out of the models are really useful at showing the depth of water throughout the city at the street level so that we can, just make better data-driven decisions around the city.
These are two standard active remote sensors.
This is an example of a pressure transducer water sensor, and what we've been trying to do is compare data like NASA satellite imagery to see how it compares to the accuracy that we're getting at the street level. So when you put it all together, it's very valuable.
One of the main applications is really trying to see, before these events happen, where are going to be the problem areas in our communities.
Determine what roads need to be closed or intersections need to be closed when.
Where these projects should be permitted. Will this building last the 30-year life of the standard mortgage? Our models, as a representation of reality, have to be as accurate as possible. The additional information from the NASA satellites, Landsat, Aster, and MODIS, really helps us calibrate our model.
Having that regional water depth map really helps us in kind of understanding what the future day-to-day looks like in Norfolk with sea level rise.
And so better understanding sea level rise will help you decide places where you may wish to work or live in the near future. It also helps you better understand specifically what your risk is inherent, not just with flooding, but also with the changes to our climate as our world continues to change, either for the better or worse.
From the vantage point of space, we are able to monitor and see changes across our planet and compare data over time. Joining us now is Dr. Nasser Sha'at, SWAT Payload Systems Engineer Lead, who's going to tell us more about how we study oceans from space. Thank you for joining us.
Thank you for having me.
It's a pleasure to have you. So let's get into it. We know that NASA uses satellites to study our planet, but could you give us a better idea of how these spacecraft actually work, specifically Sentinel-6 Michael Freilich?
Yeah, so NASA has a wide range of Earth science satellites that actually study Earth in very different ways. But first, I would like to start by saying that we're not relying on optical measurements because they can be impaired by the weather conditions or even by clouds or whether we're the day or night. So instead, we're mainly using microwave instruments which are not being affected by these conditions or whether it's the day or night. So Sentinel-6 specifically uses two main instruments. The first one is the altimeter, which is an active instrument. Active instrument means that it actually transmits power. Passive instrument means that it's only looking at what's coming at it. So the altimeter actually sends a pulse. The pulse goes and bounces back the surface of Earth and comes back to the instruments. So we know the precise orbit of the satellites, and we also know how long it actually took for this pulse to travel back and forth. And so we can actually extract the surface height by doing so. However, it's a little bit tiny, more complex than that, because this pulse can actually be slowed down by the atmosphere. So as a result, we have a radiometer, which is a passive instrument that is only looking at specific frequencies and power coming at it, which allows us to know how this pulse is being affected. So that allows us to calibrate the result that we're getting from the altimeter, allowing us to get a very precise measurement of the surface height. That's how Sentinel-6 works.
Wow. I hear that and just think we've got a lot of incredibly smart engineers working for Team NASA, yourself obviously included. So one thing that I thought about, and maybe others have thought about this too, is that if the ocean is constantly moving and constantly changing, how are we able to capture accurate measurements?
That's actually a great question, and my friends consistently ask me the same question. So trying to answer that question all the time, I realize that it's because people have in mind the fact that we're looking at a single point. So if you're looking at a single point that is constantly moving, so of course it makes it very difficult. However, what the altimeter is actually looking is a footprint on the ocean that is actually quite large, several kilometers. So as a result, small variation as a result of waves and things like that will not really affect this result, since we're averaging over such a large area. And also I should add to that the other spatial temporal resolution is really what we care about. So Sentinel-6 will be able to cover the entire map, actually 95% of the map of the globe every 10 days. So we'll be able to get this data point every 10 days for a duration of the mission, which is 5 years, until the next satellite goes, and it's going to be 5 years at all again. So the scientists are looking at a very changes over a large amount of time, so many years.
Right. Yeah. So it's not just about one wave at one moment. It's about, the big picture over a long period of time on an average. Yeah, that makes total sense. So now I want to talk about something that's probably very near and dear to your heart. We've been talking a lot about NASA's next ocean monitoring system, Sentinel-6, but I understand you're actually working on a new Earth observing mission called SWOT. And before we get into you telling us what SWOT is about, can you actually tell us what that acronym means?
Yes, so SWOT means Surface Water Ocean Topography. And topography is a fancy word to define the study of the shape of what we're looking at. And so the way SWOT works, it's basically we're using the same instrument that Sentinel-6 is using. So there is a large heritage from Sentinel-6 and the Jason series satellites. But on top of the altimeter and the radiometer and all the instrument to provide a precise orbit measurement of the satellite, we also have a very, very fancy radar. I'm not going to go into the details on how this radar works, but what you need to take out of that is that this fancy radar allows us to get inland measurements. And also, for the first time, that's going to be the first time a satellite will be able to get inland water measurements.
That's huge.
Yes. And also, it will be able to give us information about the currents on the ocean. And on top of that, will give us a better range resolution and discrimination of few meters. So we're pushing the limits of what we're capable of doing with current satellites every time. So satellites is a good example of that. We're always pushing the boundaries of what we can do.
Well, you heard it here, folks. Our team is producing the latest and greatest with whatever they do, and right now it happens to be an amazing ocean monitoring system. But that's about all the time we have. Thank you so much, Nasser, for joining us.
Thank you for having me. My pleasure.
And thank you for joining us at home. If you would like to learn more about our global ocean and sea level rise research at NASA, please head over to sealevel.nasa.gov. For more information about the Sentinel-6 Michael Freilich satellite and sea level rise, and for ways to watch the launch with us, follow @NASA Earth on Twitter and Facebook. Until then, we'll see you next time.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather.
Juliet Oscar November calling. NO1SS, Juliet Oscar November calling. NO1SS, it is 6 Juliet Oscar November. You copy me, Chris?
Copy you loud and clear.
Okay, I'm going to patch them through. Please 1 minute.
This is Owen. How has seeing Earth from its orbit affected you, in your frame of reference when moving around the ISS, or in your perspective of humanity as a whole? Over.
Hi, Owen. That's a great question. Seeing Earth from up here it's a beautiful thing. It's just this peaceful place with no borders there, and you just see this wonderful colors of blues and greens and browns and white clouds and snow-capped mountains. And it really gives you an appreciation for Earth as a spaceship for 7 billion people, just like our spaceship is keeping us alive, and how we need to take care of Earth because it takes care of us. Over.
This is Spencer. What happens if you vomit in the space station? How do you clean it up? Over.
Well, hi, Spencer. Fortunately, we are prepared for vomiting in space, and we bring special bags that if we're feeling the urge to go, we use these bags. Occasionally, on the launch, it can surprise you, and but we have bags in the launch vehicle as well. If you didn't make it in the bag, it would be a real mess, and it would go everywhere. It would take quite a bit of time to clean up. Over.
This is Lucas. How has the COVID-19 pandemic affected you while you're in space? Over.
Hi, Lucas. The pandemic has affected us because it's affecting our families. Our daily life here on the space station is largely the same with or without the pandemic. We are safe and we are executing our job and keeping the space station running and functioning and keeping ourselves healthy with our daily routine. But we're concerned for our friends and family and loved ones because they're in Russia and in the United States having to deal with it just like you are. Over.
This is Allie. What will be your first meal when you get back to Earth? Over.
Hi, Allie. I like to eat, and so I'm looking forward to any food that somebody makes. But one thing we don't have is an oven here, so something that comes out of the oven and you smell those smells and you eat a nice hot meal, that sounds terrific to me. Over.
This is Sawyer. What does it feel like when the rocket lifts off? Over.
Sawyer, when the rocket lifts off, it's this tremendous feeling like somebody's pushing you in your back and shoving you faster and faster and higher into the sky. And there's a few periods of time where our engines change, called staging, and there's some bumpiness and a little bit of shaking in the spacecraft during those periods. But the rest of the 9 minutes is just like a giant force is throwing you into the sky. Over.
This is Jordan. What does the space station smell like? Over.
Jordan, the space station has not too different smells than you'd have in a home down there. We try to keep ourselves clean. We try to keep the space station clean. In fact, tomorrow is Saturday, and that's our cleaning day, and we do our best to keep it neat and tidy. but occasionally there's smells where we have to change fluid. A lot of times that has to do with our bodily functions in the toilet, and they can be smelly there. But for the most part, the space station, to me, it smells just like a normal home. Over.
This is Eric. Was training to be an astronaut harder or easier than training to be a Navy SEAL? Over.
Well, Eric, they were totally different. The training to be a Navy SEAL initially was very hard for 6 months. Training to be an astronaut or a cosmonaut is a long process, and it takes many years of hard work. So, and it's more academic, more having to do with your brain. In SEAL training, we had some academics, but largely it was a physical thing. So 2 entirely different programs. Over.
This is Owen. What experiment that you've done had the most unexpected results? What was the expected and actual outcome of said experiment? Over.
Wow, well, that's a very detailed question. We have lots of experiments going on up here, but one that when I first arrived, we were growing some plants, and I thought that they would grow more than they did. Over the course of several weeks, they were just a small sprout, which surprised me because pictures I had never seen growth in space before on my previous missions. So I'm looking forward to trying that again and getting better results. Over.
This is Spencer. How successful is your 3D printer on the station? Over.
Spencer, we have the 3D printer has been here since I think 2015, a few years, and we've printed many parts. We don't have it deployed and active all the time, but when we need to, we can print what we need if it meets the criteria. It's a very effective way of having spare parts in space. Over.
This is Lucas. We're a model rocket building club. Did you ever build model rockets when you were young? Over.
Lucas, I wish I did, but I never had a club or a mentor in my area that was involved with model rockets, so I never really launched a model rocket as a young person, but I think it's great that you guys do. Over.
This is Allie. What does microgravity feel like when your body is over?
Allie, microgravity is more a feel of how to move around. Your body, in my opinion, feels kind of the same. Everything you do on Earth with your body, eating, going to the bathroom, sleeping, your hair growing, all that stuff is very normal, I think. But moving around in microgravity is not normal, and it takes some practice to get used to how to do it effectively. Over.
This is Eric. Does the Earth look any clearer or less polluted now compared to when you flew in 2009 or with Canadian Chris Hadfield in 2013? Over.
I actually flew with another Canadian, your Governor General, Julie Payette, in 2009. So this is my first mission in space without a Canadian crewmate. But the Earth does not look any different with our eyes than the previous times. And my crewmate and friend Anatoly has been in space several times, and we both have tried to see any differences, and we can't really tell with our eyes. Over.
This is Sawyer. Do you play any games while you are on the ISS? Over.
Well, Sawyer, we're pretty busy people up here. We have lots of work to do during the day, and by the time nighttime comes around, we just have the energy to eat and clean up from our day and prepare for the next day, maybe make a phone call or something, or answer an email, but we don't have a lot of time to play any games. Probably the closest thing to a game is seeing how straight you can fly without crashing into a wall and how far you can go like this. Over.
Well, I tell you what, for all the folks on the phone, let's go ahead and give Commander Chris Cassidy and the crew on NA-1SS a big round of applause anyway. Sending my greetings along to all of you in traditional amateur radio terms. 7 threes. Best wishes, and thank you for participating in this activity. Thank you, everybody. This is just excellent.
And with the number 1 overall pick in the Kennedy Space Center NFL Draft, NASA selects Jacksonville Jaguar quarterback and aerospace engineer Josh Dobbs. Next on the Rocket Range.
EGS Program Chief Engineer, verify no constraints to launch.
3, 2, 1, and liftoff.
Welcome to space.
NASA's internship program now has an NFL quarterback in its ranks. Josh Dobbs of the Jacksonville Jaguars has a degree in aerospace engineering, and thanks to the NFL Players Association's externship program, he is now working as an intern at the Kennedy Space Center in Florida this offseason. Josh took a few minutes out of his hectic schedule to share his unique insights on NASA and life in the NFL. Please note, this was recorded in studio prior to the current social distancing guidelines. I'm here at Kennedy Space Center in the audio booth with Joshua Dobbs, NFL quarterback for the Jacksonville Jaguars. Thank you so much for being here, bud.
Glad to be here. Thank you for having me.
Started playing football when you were 5 years old. You played high school ball for the Alpharetta Raiders of Alpharetta, Georgia. Went on to have a great career at the University of Tennessee, where you were a starter for several winning seasons in 2015, 2016, won some bowl games. You were drafted by the Pittsburgh Steelers in the 4th round of the 2017 NFL Draft. After several seasons with the Steelers, you were traded to the nearby Jacksonville Jaguars as a quarterback for the team. And what's so interesting to our audience is that currently you're doing an internship with the engineering department. Is that right?
That is right.
At NASA's Kennedy Space Center. And folks, why is that? Because Josh busted out a 4.0. Not in the 40. Of course, I don't know that
that would have been cool.
Yeah, anybody ever run a 4?
That would have been the fastest ever, right there.
Right, that's true. 4.2, right? 4.4, 4.4, yeah.
Right.
But you had a 4.0 in your grade point average and in the aerospace engineering major at UT. Is that right?
Yes, sir.
Bringing the brains and the bronze.
Brains and the bronze, yes, sir.
I love it. Well, so tell me, Joshua, you're here doing this internship. Kind of help me understand how you've been able to play football and keep a fascination with space.
It's been definitely a process. When I was younger, I attribute a lot of my success and habits I created to my parents. I grew up an only child, so quickly at an early age, they kind of taught me, one, obviously excel in the classroom. That comes first, but then they also pushed me to doing different experiences, participate in different activities that I would enjoy outside of school. So they helped me figure out that I love football by placing me in just about every single sport you could place your kid in when he's 5 years old. So, the different experience that I had growing up and being able to juggle football, baseball, basketball, along with taking accelerated classes and then being in the band. I was in karate. I was in chorus. I learned I couldn't sing, but I was in chorus.
Oh, yeah? You can sing, huh?
I can't sing. Cannot sing. Cannot sing. So don't put me on the spot.
But you took chorus to find out.
To find out, right. Okay. So I did all of those, and I kept up with extreme workload from elementary school, middle school, high school. So as the stage grew and things got more difficult, the habits that I created when I was younger or what I was able to fall back on when time management was key in college. Being able to juggle playing SEC football at the quarterback position and then also being an engineer definitely called for long days, long periods.
I can only imagine.
Yeah.
SEC quarterback, starting quarterback
yes,
for the Tennessee Volunteers, and at the same time in the aerospace engineering school. Like, how did you do that?
Well, I'll be a fool to one say that I did it by myself because Tennessee gave us a great framework when we got to school with different study halls and giving us different tutors and mentors that are in our field so we're able to learn and learn the way of the land. But also it took, determination. I think, on a daily basis, you're in class from 9 till 2, then practice is from 2, then meetings are from 2 to 4, practice from 4 to 6, then you have post-workout, post-film, and then you're in study hall, and then you're to the library, and then you wake up and repeat process the next day, and you have to eat throughout the day. So I think I closed down the library just about every single day of my college career. But again, it was the habits that I was able to form when I was younger, learning how to manage my time, be productive, be disciplined, and understanding when I came to college, I came there for a reason that, hey, I want to play football at the highest level, but I also want to pursue an engineering degree that I know that I will enjoy. It's something that I'm very intrigued with. I want to learn more. I want to be an engineer. So being able to juggle two things I was extremely passionate about, made it not suffering, but made it very enjoyable.
Fascinating. People are going to be so amazed to hear that how you juggled all those things, but you give credit to your parents who kind of helped you instill some good habits in you at a very young age, which is pretty cool. What are you going to be doing here at KSC?
So thus far, it's been pretty much a whirlwind of a week. I started off in the KEXI division where I was working in instrumentation. Spent a day, shadowing them, seeing, the hazardous gas detection system, learning about the wind profile that they have for launch day, just learning about the weather protection system on the mobile launcher. So just seeing different things and understanding how the instrumentation works from an electrical point of view. And then from there, it's kind of been every single day, it's been a different opportunity where I've gone from there to I've gone to flight accessories, so seeing the different umbilicals, how they work, how they secure the rocket to the mobile launcher, to seeing different tests that they're performing on the instrumentation, to then learning about the core stage and how it's going through the screen run testing. And
talking about the SLS, the next generation world's most powerful rocket that we're going to use to send people back to the moon.
And then to Mars.
Yeah.
So it's been a whirlwind. I've learned about the SLS, the whole space program, the Artemis project, Orion, which goes on top of SLS.
Mm-hmm.
So it's been a whirlwind of a week. I've kind of seen, I think, all of KSC, but I know the next couple of days I'll continue to see more, and I'll continue to have my mind expanded by what's going on here. And it's truly amazing to see the innovation that's going on a daily basis.
Absolutely. And the space history that's here when you're told that, this is where the rockets took off and took Americans to the moon for the first time. What's your sense of the history here?
That's so humbling because I'm connecting with the history just because, just growing up, being so interested in engineering, the history is what you look up every single day. You're like, oh, wow, this is what we're doing. This is where we've come from. So then to be able to be here on the footsteps of where it all happened, where the innovation happened, where the science happened, where the engineering happened, and where the launches actually took place to take the people first to space and then to the moon, now to the International Space Station, where they'll take place to go to Mars. It's kind of, it sends chills down your back. I honestly, driving in every single morning and just seeing, because I'm at OSB 1, so it's the one right next to the VAB.
Right.
So
and
driving
the vehicle assembly building, the iconic building
building.
Yeah.
Driving in and parking in front of that building every single day, it really wakes you up when you get here. You get here at 7 a.m., but you get out of the car and you see that. It's like, wow, there's so many people that have come before me that have paved the way to what's going on here at NASA now. So just to, I know I'm not here for a long time, but to be here and just get a glimpse and be able to touch, what's going on here, it's truly an amazing experience.
Now, you've only been here a short period of time. And for those who, if you've never met Josh Dobbs, he comes across, I just met him a few, minutes ago, but you come across as a very polite, very gracious with your time kind of person. But now you're coming in as a professional quarterback to a lot of people who are engineers, who might be big football fans, fantasy football fans, whatever, right? They're going to be like, oh, dude, can I have this? Are you going to get any work done? How do you kind of give them a little stiff arm without being rude?
You obviously, you give them both. Everyone wants to talk about football. I mean, It's like America's favorite pastime, and we're in football central USA right here. Yeah. So everyone loves talking about the game, which I don't mind. I love talking about the game. But the first couple of days, I also say, I'm here to learn the life of an engineer because that's also part of who I am. I'm an engineer. I studied aerospace engineering, so I want to see the day in the life of an engineer. So it's funny. The first day we were mapping out, everything that I was going to do here, and they were saying, "Oh, you don't want to go to the meetings. Let's just show you the cool stuff." I said, "Okay, I want to see the cool stuff, but also,
but truly,
I want to sit down on the engineering meeting where you're discussing different things that are going on with the projects and different instrumentation that you have to test. I want to see the logistics side of it to understand what it means to be an engineer. Maybe I'm sitting there shadowing you doing your desk busy work, but that's still interesting to me because I want to see, not being able to be around this field a lot in the real world, I want to see what it's like to be an engineer for a day. So I kind of taking it all in, whether it's the cool stuff where you're at the VAB, the vertical assembly building, where you're at the pad, where the launch pad, or whether you're just sitting in the office doing normal desk work, it's all
You wanna see it.
It's all enjoyable to me.
You mentioned meetings. Now NASA likes meetings.
They do like
we've got meetings. We got to have
meetings and acronyms. I've learned that quickly. Those are two hot topics here for
Almost
sure.
like another language.
It is.
You speak.
I started looking up the dictionary online. I'll just write down acronyms in my notebook and then just look it up online and then go home and that's
Later,
what they were talking about.
like, okay, now I know what it's
Now
talking
I get it. Now
Don't ever be afraid to ask for acronym because everybody knows it out here. Like,
Right.
you know, hey, you got to get this figured out. Well, so what about the pro football part? I mean, right now you're a professional quarterback in the NFL for the Jacksonville Jaguars. So what's your goals? What's your aim there?
I am there. So obviously I was traded from the Steelers to Jacksonville at the beginning of last season due to injuries and then logistics, and then also the NFL is a business, so you have to respect that side of it as well. And my goal is to be a starting quarterback in the NFL. There's only 32 of them, and I want to be one of those 32. So that's what I'm working for every single day. It's funny, you go from engineering all day to then going over to the gym. You got to get your workout in. So days obviously can get stretched out, but it goes back to college. I understand how it is to juggle both sides of it. How is it to work toward a dream, to work toward a goal. So every single day I'm stacking chips, whether it's right now in the engineering world, but then also making sure I'm getting my training, my conditioning to be able to be prepared once our off-season regiment starts in April. Hit the ground running and be able to go in and dominate once the season comes.
Oh, I love to hear that. Well, so these two goals here, becoming a starting quarterback in the NFL and then possibly an aerospace engineer, it's tough to imagine how you can keep that going forward. But to be clear, very difficult to get the internship. So how do these two branches keep them going at the same time?
Well, of course, right now I'm a professional football player, and that's my focus. But the beauty about being a professional football player in the NFL and the NFLPA is they provide you with opportunities like this, an externship, where you can go and take 3 weeks of your time in the off season to immerse yourself into a field of your interest. So to have these 3 weeks to immerse myself into the engineering world is amazing. And then once this finishes and we're back to the grind where you're back on your training regiment every single day, throwing, lifting, running, you're taking each year and you're just building chips. So obviously like most interns, I'm not able to spend an extended amount of time, but I'll be able to have this opportunity to first learn everything that's going on at KSC, be able to see the big picture and see different subsystems, and then next year I'll be able to grow on that. So obviously, people think of like goals and they want instant gratification. Like, all right, I got to do both now, right? So I'm working on one now and then playing the long run for the other one. So it works out pretty well, just seeing the big picture.
Taking the small pieces step by step to get your goals. You're right, because it's very hard to realize a big goal like becoming an aerospace engineer all at once.
Especially at NASA, right?
Right. So what do you think about the new Artemis program? This is the one where we're seeking to land a woman, the first woman and the next man on the moon by 2024. That's just 4 years away. When you hear that and you know that there's going to be a ton of engineering that kind of gets behind this, we've gone on the moon before, but really going to the moon this time is to help build that
the next step,
right, for Mars. So what kind of what do you think about a goal that big that NASA has set?
I think it's amazing. I think it's been a while since we've gone to the moon, and obviously there's a lot of reasons behind that. We were building an International Space Station, we were doing other missions, but for that to be a goal and just to see how that goal is basically the framework, the support to the next goal, the springboard to go into Mars, I think is extremely exciting. And I think the most interesting thing that I've seen on a daily basis is when you go out and you're a part of the different subsystems and you're interacting with the different engineers, the stuff that they're doing when they're building the mobile launcher and when they're assembling this rocket, it's stuff that's never been done before. That's what's so amazing about it. It's not like they're coming here and mass producing a piece that operates on a daily basis. They're literally building a rocket to do something that it's never done before and that has never been done in mankind. So it's special. It's special, right? It's almost mind blowing. It's like, wow, like it's like something you see in movies. It's truly mind blowing. So,
I often find myself when I'm walking around the Space Center, particularly inside the VAB, and I'm looking at those massive structures. Like, I feel like I'm on the set of Star Wars.
Well, you know the movie Pacific Rim where they have like the gate? That's what it feels like. The ginormous ceiling, Star Wars as well. You're walking around there, you're just like a kid in a zoo almost. You know, It's amazing just because of the innovation, and then being able to like have an engineering background, just knowing what it takes. You know, it's taking stuff that you learned in school, stuff that you've learned on the job, but it's also being able to use those and critically think to solve problems that have never been solved before.
There's such a reward to that, isn't there? I think that's kind of like what's central to engineering is having a problem and finding that unique solution. Is there a particular type of problem that you would enjoy helping NASA solve?
Honestly, you know, any problem. It was actually interesting. Yesterday I was over with the virtual reality team where they take your body dimensions and they immerse you into different environments. So like whether you're like an astronaut or someone working on the mobile launcher, you can see the stuff like actually work, you know, in the space, right? So I get a chance to spend extended time with them a little later. But that was so interesting because I'm thinking like, just how applicable that is to like every situation, whether it's here at NASA or in sports, like just virtually seeing yourself in different situations and being able to take those mental reps. So whether you get out on the mobile launcher and you're trying to make an adjustment, or you're an astronaut trying to just fit in the spacecraft, you know, there's so many applications for that software, for that technology, and I think like really the sky's the limit for that, just visually be able to virtually see stuff and get mental reps at it. So it's definitely interesting.
All right, Joshua Dobbs, you're working some long days, interning by day here at Kennedy Space Center and getting ready for the NFL season coming up as a quarterback for the Jacksonville Jaguars. We wish you great success, and we thank you very much for being here. And listen, you know, we know you're going to be fantastic, but if someday down the road, when you leave the NFL and you decide to come to NASA Kennedy, we got dibs on you for the flag football team, all right?
That's the deal.
We got a deal?
No other NASA site will stand a chance.
Oh, that's what I'm talking about. Joshua, it was a pleasure.
Thank you.
Thank you very much.
Thank you for having me. I appreciate it.
I'm Daryl Nail, and that's our show. Thanks for stopping by the Rocket Ranch. And special thanks to our guest, Joshua Dobbs. To learn more about NASA's intern program, visit intern.nasa.gov. And to learn more about everything going on at KSC, go to nasa.gov/Kennedy. And check out NASA's other podcasts to learn more about what's happening at all of our centers at nasa.gov/podcasts. A special shout out to our producer, John Sackman, our sound man, Lauren Maythree, and our editor, Michelle Stone. And remember, on the Rocket Ranch,
the human exploration of space is still in its infancy. The Apollo missions were just the first step in our goal to have astronauts working on the surface of worlds beyond our own. And as NASA plans its return of humans to the moon and eventually onto Mars, a team of scientists have come together to test and build some of the tools our future explorers may use on these journeys. Based out of NASA's Goddard Space Flight Center in Greenbelt, Maryland, this group is called the Goddard Instrument Field Team, otherwise known as GIFT. The scientists in GIFT collect data on some of the most unique terrains on Earth, such as glaciers in Iceland, lava tubes in Hawaii, Mar craters in New Mexico, and the desert regions of Chile. The goal is to conduct field research in geologic settings that share similarities to locations on other planets, moons, and even asteroids. Scientists call these sites planetary analogs, as they help us learn how to interpret data from across the solar system, while also getting a better understanding of Earth. In these environments, GIFT researchers test both commercial and newly developed scientific equipment. These are portable devices that could be used by astronauts, or used aboard future rovers or other types of spacecraft. These field instruments are capable of multiple types of analysis, with some providing instantaneous feedback. The team uses devices that can observe and characterize the landscape around a user, as well as ones that analyze the chemical composition and physical properties of materials found at and below the surface. The team also works with instruments that measure aerosols in the atmosphere, magnetic fields, and solar radiation. No matter which field campaign they are on, the scientists in GIFT are selecting and using their instruments to answer high-priority science questions. And to more fully capture the essence of how humans would explore the surface of the Moon or Mars, GIFT members also simulate astronaut EVAs, or extravehicular activities, at the planetary analogs they study. Both former and current astronauts have accompanied GIFT on these simulations. Overall, the Goddard Instrument Field Team provides a unique resource to NASA and the external science community by combining the studies of planetary science, earth science, and hardware technology. All of the tests, experiments, and data collected provide a blueprint for the human exploration of other worlds. And that's a great gift for those taking the next giant leap.
Station, this is Houston. Are you ready for the event?
Houston, this is Station. We are ready for the event.
Houston ACR, this is Mission Control Houston. Please call Station for a voice check. Please.
Station, this is Houston ACR. How do you hear me?
I've got you loud and clear. How us?
Loud and clear.
Good morning, and congratulations to the entire Nettleton STEAM Schools community as you prepare to downlink with NASA astronauts aboard the International Space Station. This is the first time a school in Arkansas has been chosen for this honor, and it's a real testament to the hard work and curiosity of the students, as well as the innovative ways STEAM's educators have incorporated the space program across your entire curriculum. I'd also like to acknowledge Arkansas State University and all the partners in the Jonesboro community who've helped make this happen. And of course, I want to thank Kate Rubin, Shannon Walker, and all their colleagues aboard this space station for their service and their extraordinary efforts to expand our understanding of our universe and ourselves. It was a great honor for me to work with the men and women of NASA when I was president, including on the creation of the International Space Station. I'm proud that by the time I left office, we'd launched the Unity module and had our first international crew reside on the station. And I'll always be glad that I sent the first presidential email to space to my good friend, then 77-year-old John Glenn, as he was aboard Space Shuttle Discovery. Our technological capabilities have grown exponentially since then. And that's what makes the work of the International Space Station and Nettleton STEAM both very exciting and very important. With a great education in the STEAM fields, America's young people can help us keep pushing the horizon of our knowledge and understanding further and further for many years to come. I can't wait to see what you'll discover. So again, thanks and congratulations to everyone who's helped make this day possible. Have a great conversation, and my best wishes to all of you for much more learning, exploration, excitement, and success.
Hello, my name is Patrick Taylor, and I am a 5th grader from Nettleton STEAM in Jonesboro, Arkansas. My question is about the future Artemis missions. How will the difference in microgravity on the Moon versus on the International Space Station impact Planck growth chambers?
Hey, from the International Space Station. That is such a great question. We actually have been doing plant growth experiments up here just this last 3 weeks. So we have a lot of plant growth experiments on board the International Space Station. One of the things that we've really worked on in microgravity, which is where we are right here floating, is how to water the plants. So the water floats up, it kind of wicks along the stem and the leaves of the plants, and it doesn't go to the roots in microgravity because everything floats. So we think that on the moon, we're going to have 1/6 of Earth's gravity, and that's actually going to help us grow plants a little bit better. It's going to bring the water down to their roots, and it's hopefully going to allow us to grow plants on the moon. We can grow them pretty well in space. I grew some radishes, and we even harvested them. Shannon got a chance to see, and we've grown many other kinds of plants on the International Space Station in microgravity. It just takes some special equipment. Great question.
Hello, my name is Emily Perez, and I am a 4th grader. The new Artemis expedition will involve the first woman and the next man on the moon. What will be the significance of being the first woman on the moon?
Hey, thank you for the question. It's a really exciting time for the Artemis program at NASA. And as you can imagine, there's a lot of people that are thinking about this and they're talking about this. And for Shannon and I, we get asked this question a lot. What's it like? What's it like to be the first in your class to do something? What's it like to be one of the only females in a graduate school program? Those kinds of things. I would say we don't think about it that much. We don't spend a whole lot of time thinking about the fact that we're women and we're doing something. We're just people and we're just doing what we love. So I think that there will be a significance. There's going to be a significance for a lot of kids growing up who are able to look at the moon and to know that we have people walking on the moon. That was just this absolutely critical moment a few generations ago, and I'm really excited that your generation is going to get to see it. And so I think the significance is that we're going to the moon, we're sending people, and we're doing this with your generation. You guys are the Artemis generation.
Hello, my name is Genesis Choywick, and I am a 3rd grader from Nettleton STEAM in Jonesboro, Arkansas. My question is, what specific things are you going to study during your time on the International Space Station?
Well, goodness, we are studying so many things on the International Space Station, it's really hard to capture them all. We've got studies going on in biology, we've got studies going on in material science, we've got studies outside looking at the Earth, looking at the universe. So I think some of my favorite studies, though, are the ones that involve the human body. It's really interesting to me to understand how the human body reacts to being in space, because there are some changes that happen, and so we need to understand them, especially if we're going to spend more time in other places, on the space station, on Moon, hopefully on Mars and other places in the future.
Hello, my name is Sam Sawyer, and I'm a 5th grader. My question is for Dr. Rubin. I read that we were the first astronaut to sequence DNA in space. What were the challenges of sequencing DNA in microgravity?
That is such a good question from a 4th grader. I'm so impressed that you read about sequencing DNA in space. It was incredibly cool. I have to say, the first time we sequenced DNA, and we are even working on this expedition in 2020 on sequencing more DNA in space. Some of the challenges are, like we talked about with plants, that fluids behave differently up here. So if you have a fluid on the Earth and it gets a little air bubble in it, the air bubble always goes to the top of the tube. In microgravity, it doesn't. It just stays right there. And so we didn't know how this was going to affect our equipment. So this was our very first chance to test this equipment out in microgravity on the space station. And we actually found that everything worked pretty much the same as Earth. The small bubbles don't bother this kind of equipment. And so this really opens up the world of sequencing in space for the future.
Hello, my name is Aiden Toturo, and I am a 4th grader from Nettleton STEAM in Jonesboro, Arkansas. We have been constructing and researching robotic arms in our 4th grade class. What is the significance of astronauts using the Canadarm2 on the International Space Station?
Aiden, fantastic question and very exciting to study robotics. You know, I studied robotics a lot in my career with NASA. So I think the significance, the main thing is we would not have a space station without the Canadarm. It was used to construct the space station. We took pieces out of the shuttle payload bay and we attached them to the pieces in orbit on the space station. So it was absolutely vital. Now that the station is constructed, we use the arm to do experiments on the outside. Sometimes we need to move equipment outside from one place to another, and sometimes we need to capture our cargo vehicles that are coming up and attach them to stations so we can get provisions up here. So there is no way we would have a space station without a robotic arm.
Hello, my name is Allison Moss, and I'm a 4th grader. My question is, can you show us how you drink water in space and how water behaves in space?
Hey, Allison, that is a great question, and we have a lot of videos, actually. If you go to nasa.gov, there are a ton of videos there. It shows you how astronauts drink water in space, and we even have a video with some really big tanks of water. They're clear, so you can see the water move around. I had a really fun experiment that was looking at fluid dynamics, and this is the question that you were asking, is fluid dynamics, the properties of fluids in space and in microgravity. So go check those out, and I bet you're going to be amazed.
Hello, my name is Bryson Gann, and I'm a 3rd grader at Nettleton STEAM in Jonesboro, Arkansas. In 3rd grade, we have been learning about water filtration devices. Can you tell us how your water filtration device works?
Wow, water filtration in 3rd grade. That's amazing and awesome. So, yes, we filter our water out here. We take all the liquids that we have and clean them up so we can drink them. And so what does that mean? We actually take our urine. We take the sweat that comes out of the air that goes into the humidity. We take anything that we can find. We get into a tank. We typically sort of heat the water so it evaporates, so just the clean water evaporates off and all the nasty stuff stays behind. Then we take that clean water and we actually make it even better. We filter it, we put some iodine in it to kill any bacteria, and it comes to us as pure, clean drinking water. It tastes pretty good.
Hello, my name is Amelia Westman Forbes, and I am a 6th grader. My question is for Dr. Shannon Walker. What is the routine you follow each day on the International Space Station?
Oh, what's my routine? Sorry, it was a little hard to understand. So it's actually pretty interesting. Each day is different up here. We typically get up about 6 in the morning. We have some time to read our schedule for the day, to eat some breakfast, and along about 7:30 in the morning, we start talking to the control centers all over the world. We talk to Houston, we talk to Huntsville, we talk to Moscow, we talk to Europe, we talk to Japan. We get instructions from them on what we need to do each day. So when we get up and we see our schedule, sometimes we're doing maintenance on the space station, sometimes we are doing experiments, we're doing a lot of those, and recently we just had a cargo ship come up, so we've been doing a lot of unpacking the cargo ship to get more science on the space station. We do that all day long, we get a little break for lunch, and then about 7:30 at night, we go around the world again and talk to all the ground control centers again. They tell us anything we need to know for that day or for the next day. Then we have dinner and we go to bed and get up the next day and do it again.
Hello, my name is Layla Westbrook, and I'm a 6th grader from Nettleton STEAM in Jonesboro, Arkansas. My question is for Dr. Kate Rubens. Can you talk about any interesting experiments that you have worked on in space?
Layla, I can tell you are a scientist in the making. That is a great question. Yeah, we have some great experiments. So this morning and this afternoon, I was working on a really interesting experiment. It's called Cardinal Heart, and it's actually taking a cell type called cardiomyocytes. So these are the kinds of cells that are in your heart. we can actually take those and grow those in special chambers in microgravity. It's amazing. Yeah, it's really cool. And we're trying to see what the differences are between cells that are grown in space and cells that are grown in Earth. So you can imagine there might be some differences. So we're going to send, some of these cells are going to live on board the space station for 30 days, and we're going to send them back to the ground, and then we can compare the two different kinds of heart cells.
Hello, my name is Olivia Exum, and I'm a 5th grader. My question is, what hasn't been accomplished in space that you would like to see happen within the next 5 years?
Well, that is a wonderful question. There are so many things that can happen in space, but what I think would be really neat to see in space is for us to have other space stations and places for tourists and ordinary people to go visit space. Right now, you can see we sort of live in a laboratory, and there's a lot of work that gets done here. Sometimes it's just hard to enjoy, and it's just professional astronauts that get to come up here. So what I would like is for ordinary people to be able to go into space.
Hello, my name is Brooklyn Wheely, and I'm a 6th grader from Nettleton STEAM in Jonesboro, Arkansas. My question is for Dr. Shannon Walker. What changes have been observed in the human body during a long-duration spaceflight?
You know, it's really interesting how the body changes when it goes into space. One thing that happens immediately is your spine grows, so you get a little bit taller when you're in space. Yep, exactly. Some things that we have seen that we're still studying is we've actually seen changes in people's vision when they're in space. We don't know why that is, but we're certainly studying it. We've actually seen changes at the DNA level, I believe, and the cellular level that we're still studying. We see that people have a lot of bone loss in space, and so we exercise a great deal to prevent that so that we're healthy when we come home. So there's a lot to study about how the body reacts in space.
Hello, my name is Nakinia Smith, and I'm a 5th grader. My question is, what variables affect plants' growth in microgravity?
Hey, Nakinia, that is an awesome question. And so we're studying that very thing up here. We have done a whole series of plant experiments, and some of the variables that we find that are really critical for plant growth are the atmospheric conditions. So you might have studied about plants. They like to absorb CO2. CO2 is not good for humans. We produce a lot of it, but we don't want to breathe a lot of it. But plants love it, and they need it. And so we've studied plants up here and determined that they really need a good atmosphere, and we can separate the plant atmosphere from the human atmosphere. So we can give the plants a lot of CO2, and we can keep the CO2 away from the humans, and this is really good for plant growth. The other really critical factor is, of course, water. Plants love water. They need water to live. And so how we provide water to these plants is really important. The water has to be provided in a very special way so that the plants can still grow in microgravity. And the third thing is, of course, nutrients. So plants, just like people, they need food and they need water. So how you give plants nutrients on orbit is actually pretty similar to the ground. They need very similar kinds of chemical composition. They need light and they need nutrients in their soil to grow. Great question.
Hello, my name is Carter Massey, and I'm a 4th grader from Nettleton STEAM in Jonesboro, Arkansas. My question is for Dr. Walker. What skills outside of STEM, particularly science, are needed for long-term space travel?
Carter, excellent question. A lot of people think it's only about science and engineering. I think there's two critical skills that people need for long-duration spaceflight. I think you need to be a really good team player, and I think you need really good communication skills. The reason is the following. So we have our crewmate team that we have to work with and we live with every day. So that could be months on end. So you've got to be a team player to get on with your crewmates. But the bigger team is the people on the ground that are working the mission with you. It could be hundreds or thousands of people. You've got to be able to work with them, understand them when they send you information that you need to know to do your job. So team players one. Communication is the other. Communicating with each other is very important, so you don't get angry with each other, just like with your family. You got to communicate just right. Communicating with the ground on the science and engineering that you're doing is hugely important. You're doing experiments for scientists that aren't with you, so you've got to be able to tell them what is truly happening. And then finally, if we're going on long duration flight, you've got to be able to communicate with people around the world so that they can understand what you're experiencing, because you're experiencing everything for them. And so that's why I think communication and teamwork are the two skills you need.
Hello, my name is Jack Patton and I'm a 6th grader from Nettleton STEAM in Jonesboro, Arkansas. We designed a pressurized spacesuits in our 6th grade class, and we are curious about how the spacesuit feels whenever you're out of the space station wearing it. Could you please tell us this?
Hey, I can't believe that you're designing spacesuits in 6th grade. I wish I could have done that in 6th grade. That's really amazing. So the spacesuit is actually like its own personal spacecraft. It has to keep the human alive outside the space station. So we have to deal with things like being in vacuum. We have to have a pressure garment. We have to keep the human either hot or cold on the right side of the temperature, because the temperature swings from really hot to really cold. We have to deal with radiation. There's radiation outside the space station. And we have to be able to deal with things in microgravity. So we have to not float away from the space station. This is rule number 1 of spacewalking, is don't float away from the space station. And so all of these things combine to make a pretty big and a pretty bulky suit. We train a lot in this suit, and actually it feels pretty much like training in the ground. The suit's about 300 pounds total, and you have to move this suit around as you're floating outside the space station. The things that are different are that you actually float in the suit. So this feels a little bit better than it does when you're in gravity. And the other thing is that everything around you is floating. So you have to deal with all the tools and all the equipment in kind of a different way than we do when we train underwater in the swimming pool. So I am really looking forward to us wearing a spacesuit that you design someday.
Hello, my name is Arina Shinova and I'm a 3rd grader. We've researched that day and night changes every hour and a half. How is this occurrence affecting your sleep patterns?
You know, that's an interesting question, because a lot of people do ask that, since we do go around the Earth every 90 minutes. But the funny thing is, if you look around us, you don't see a whole lot of windows. We do have windows on the space station, but we don't see them. We have to kind of go and look out the window. So our life up here is kind of like living in an office building on the inside. So you don't really notice the day-night cycles so much. And in our crew quarters where we sleep, we don't have windows at all, which is really sad. I would love to have a window in there.
I would like a window.
So as much as it would be interesting to say that it affects us, it really doesn't affect us at all.
Hi, I'm Governor Asa Hutchinson. I remember the amazing moment on TV when I watched an American astronaut become the first man to walk on the moon. Here we are 50 years later, and students can talk to astronauts in the International Space Station. Thank you, NASA and all the astronauts, for giving the students at Nettleton STEAM and all across Arkansas this amazing moment.
Station, this is Houston ACR. That concludes the event. Thank you.
Thank you to all participants from Nettleton
Thank you,
STEAM
Houston.
Station. We are now resuming operational audio communications.
Hi, my name is Jeff Bittner, and I'm a logistics specialist on the rocket train. This is rocket science in 60 seconds. Northrop Grumman is the manufacturer of the rocket boosters for NASA's Super Heavy Lift rocket, the Space Launch System. And we transport the boosters the same way we have for 3 decades, rail. The 21-car rocket train uses 2 engines, each producing 6,000 horsepower, to travel through Utah, Wyoming, Nebraska, Kansas, Missouri, Oklahoma, Alabama, Georgia, and Florida. That's a stretch of 2,800 miles over 3 railroads to deliver the motors to Kennedy. These rail cars are built to carry the immense weight of the 180-ton segments. It takes an entire day to load one segment on one rail car. Each segment is enclosed in a clamshell-like covering to protect it during travel.
Let's hear it for the world-class NASA STEM Stars team. From NASA centers across the country, we present Dominic Lundy. Hello, my name is David Alexander, connecting to you from the Armstrong Flight Research Center. And welcome to NASA STEM Stars, where students connect firsthand with NASA scientists, engineers, and innovators to learn more about their missions, career paths, and opportunities. As you may know, the engineering design process is an iterative process that engineers use to guide them through problem solving. NASA engineers ask questions, they imagine solutions, they plan designs, create and test models, and then make improvements based on these models. These steps all contribute to mission success here at the agency. Today, we're going to focus on the testing phase in the engineering design process. Green Run is a series of tests during which test engineers will actually test the Space Launch System, or SLS core stage, before actual launch in the future. In today's mission, we're going to meet the person who is in charge of firing the RS-25 engines. Joining us today is Dominic Lundy from Aerojet Rocketdyne. He is an actual aerospace engineer. He engineers the lead for model-based systems, engineering, and transient analysis. So we welcome you to the program today.
Thanks, David.
Awesome. Dominic is actually going to share a little bit about his background, his career experiences, and the work Rocketdyne does for NASA. So as you're listening to him share his story, we really want for you to come up with some questions to ask him. So about half of our time is going to be devoted to answering your questions. So please enter those questions in the chat throughout the conversation today, and we'll actually try and answer them before we wrap up for today. With that said, I'll turn it over to you, Dominic, to get us started.
Thanks, David. Hi, everyone. My name is Dominic Lundy, like David said, and I'm an aerospace engineer. So I work at Aerojet Rocketdyne as a system performance analyst. And I want to tell you a little bit about myself. So I went to California Lutheran University for my undergraduate. I did a physics bachelor's of science there. After I finished that, I went over to Cal Poly San Luis Obispo up in beautiful Central California. I did my master's in aerospace engineering there and just finished about a year ago.
Awesome. You have a really phenomenal education, Dominic. Do you have any time for yourself? What do you do in your free time?
I do have free time. Yes, I'm able to do a lot of fun things. One thing I really enjoy is to go rock climbing. So I'll go out and I go to the gym and practice my rock climbing. Recently, I think last summer, I got to go climb this hill above Mammoth. That was more of a mountain than a hill. I really am into road biking around the cities and mountain biking in the hills. And recently, in quarantine, I've gotten into disc golf, which is where you throw your little frisbees into baskets and try and keep a low score. I also like to do things inside. I like to do coding. I'm really adamant about coding. When I was 12, I saved up all of my money from Christmas, told everyone just to give me money, and I went and I bought a Lego Mindstorms. I got to build Legos, then I got to put sensors on them and code them to do the things I want to do, like pick up a ball or follow a line. It was really special. I also am just really into space exploration in general, and I like teaching as well. I've taught a few classes, and I'm looking forward to some more teaching opportunities.
That is really awesome. You have a whole plethora of experiences all together. I've been to Mammoth. I've been snowboarding there. Are there any other mountains you like to climb out there?
Out in Mammoth, if you go a little bit north to Yosemite, I did some of my first rock climbing there, and I also got to watch my cousin climb El Capitan, which was unbelievable to watch. It's like a 7-day climb for him. It was special.
Wow, that is totally amazing. Sounds like the triathlons of mountain climbing all together. If you add swimming, you'll definitely be finding yourself to doing that. Speaking of which, do you do any of your interests, like I know you mentioned coding, for example, do any of your interests coincide with your career?
Yeah, so I would say like coding, like you said, in space exploration, but coding really is what led me to where I am today. As an analyst, we spend a lot of time looking at lots and lots of data. And so we code different ways to process that data. We also create models of the system. So we say, if we turn this valve, what will happen? And so I code those things. And that coding has come from all the way back when I was doing Mindstorms, through high school, through college, through my master's. It's been following me the whole way.
You have an extensive array of experience, and I really love that. But for our listeners that are out there, how did you get to where you are today in aerospace?
Yeah, so I think I went through a lot of different projects to get to where I was, and I wanted to show you a couple here on the screen. On the left, you can see a project I did for summer research at Cal Lutheran. I got to code a model of a superconductor. A superconductor is this really incredible material that we like in physics, where if you bring it down super cold, I'm talking like if you touch it, you will burn your fingers because it's so cold, burn them because it's so cold. If you bring it down that low, it has complete 100% efficiency. It is perfectly solid. And it's really cool to watch the models work. So I did a whole project on that one summer and presented in front of a couple research groups. And then on the right, you can see Dawn. That's my solar car that I got to build at Cal Poly's Prove Lab. If you see over there, I am the guy in the orange vest taking care of the car. It's a solar car. So what that means is we take the sun's rays, we put them on top of the car, it turns it into electricity, which turns it right into an electric motor to make us go down a runway at 65 miles an hour. Well, almost 65. We haven't hit it yet. Yeah, that was really cool. I got to be the test lead, which means I was in charge of writing all the test procedures, and I was in charge of managing all the people, making sure we kept our drivers safe.
Okay, that's really neat. So I have a question here from a student. Student wants to basically know, At what point in your life did you realize that you wanted to be an aerospace engineer? But at the same time, I think in answering that question, you should probably also discuss a little bit more about what an aerospace engineer is.
That's a really good question. Okay, I will start with what an aerospace engineer is to me. I think to say it pretty simply, an aerospace engineer is somebody who helps to build rockets and planes. And how I got there was I actually have a very defining moment. I was doing physics for my undergraduate, which is a little bit different than aerospace engineering. And I was doing a project at William & Mary in Williamsburg, Virginia. And I remember doing this project and saying, I want to work on something where I get to build it and make like a difference for people. And so now at my wall at Aerojet Rocketdyne, I have a astronaut wall of all the astronauts who I've met, who I've gotten their signatures or shaken their hands, and of all the people who will fly on the rockets that I build.
That is very inspiring. So let's talk a little bit more about the rockets that you make. You're currently working on the Space Launch System. So for our viewers who are not so familiar with this, what is the SLS and what is it going to do for us?
The SLS is an amazing rocket. I'm so excited to work on the Space Launch System. So this is the rocket that is going to bring us to the moon and to Mars, which is just so exciting to think about, going to another planet. It's insane. I get to work on the engines on this rocket. Let me show you a little bit about what this rocket's all about. On the white there on the side, those are the solid rocket boosters. Those produce a ton of force really fast. They produce both of them together around 6 million pounds of force. In the top, the very top, is a little white part. That is the Orion spacecraft. That's where we're going to be putting humans, actual humans, on top of this rocket to launch them to the moon and to Mars. And then we've got the core stage, which is the middle orange part, which holds all of our fuel. And then right below the core stage is my RS-25, my 4 RS-25 engines. And this rocket's going to launch the next woman, and the first woman and the next man to the moon by 2024. And I'm so excited to work on it.
Yeah, that is very, very important work that you do all together. And just as important in terms of motivating our next generation of explorers. And we have a question from a student here, and the student is basically asking, what advice would you give to a student who wants to get into aerospace?
That is a really good question. I think I got a couple things. I know that I didn't know if I wanted to be in STEM when I was younger. But I know that while I was in school, I really paid attention to each and every math class because I knew each math class built off each other. So I knew I had to pay attention there, and every science class built off it. Also, like learning how to work on team projects at school was really important to me. But when I was younger, I didn't think about all that. All I could think about was how much fun science was and how much fun I had playing with it. I remember building tons and tons of baking soda and vinegar volcanoes in my backyard, blowing up balloons using the bottles, or taking a balloon on a string, launching it. I had this whole paper airplane book, and I think I went through every single one, understanding how they work. So for me to get into a career in STEM, just don't be scared of being a little nerdy or a little bit excited about science things. It's really fun stuff, and like get your friends involved and go play with things that like most other people don't play with. Maybe like trying to figure out how you can bounce a tennis ball on top of a basketball and see how high it goes and figure out why that happens.
Yeah, you definitely have the opportunity to do big things at the National Aeronautics and Space Administration. It's my little testament to the student that asked that question. But speaking of size and sizable goals and things like that, how big is the Space Launch System?
Oh, it is massive. It is humongous. I think we have a little graphic to show you, but it is 322 feet tall, which is larger than a football field, which is insane to think about. So a normal human is about 6 feet tall, and so take 6 feet, and we are only as big as the engines at the very bottom of that picture. If we can see here, only a tiny bit.
Mm-hmm.
This rocket is so big, it can launch us at 24,000 miles an hour. It's going to get us to the moon, which is over 200 200,000 miles away. Numbers that are just insane to think about, landing a rocket for 200,000 miles. That's a really long road trip. I would be asking, are we there yet? And it only takes like 2 days, but that's a good amount of time.
Yeah, definitely. Now, we have the Saturn, which essentially took us to the moon. We also have the space shuttle. So,
Yeah.
question here is that how new are the capabilities of this particular rocket compared to those other technologies?
Yeah, so I'm really excited to be working on the SLS because of where we are. We learned how to build big, large moon rockets with the Saturn V, but it had to be very, very large, and it didn't have a ton of extra capability because it was using less efficient engines and older technology. Then we went on to the space shuttle, where we built the International Space Station. We worked on the Hubble spacecraft. It's a plane that can fly into space and land on its own. It was amazing. And the engines on it, the engines I work on, called the RS-25 engines, those are the most efficient stage combustion engines that fly today. They're also our most experienced of any rocket that we have, any large stage combustion rocket that we have in the United States. It's a rocket that has over 1 million seconds of testing time. And we know this rocket, our team knows this rocket inside and out. We know how these engines work. So I'm really excited to be working on the SLS, which is taking the moon rocket type build where you have the people on the very top and a very large multi-stage rocket. But on the bottom, we've got very high efficiency engines, large solid boosters that we know work really well, making it a really reliable but also super powerful rocket all at the same time.
Okay. So I'm really excited about the SLS, especially the way you talk about it. I'm totally excited. Is this capability going to fly like next week or?
I wish. It's coming up really soon. So right now we actually have built the first core stage. That's the orange tank. We have that core stage built, and we have our 4 RS-25 engines bolted onto the back of it, or attached onto the back of it. And we have that whole core stage up in the Stennis Space Center's B2 stand. So the B2 stand is in Mississippi at the Stennis Space Center, and it's going to hold down the entire stage as we turn on the rockets. So what we do is we're going to fill up the propellants in the whole core stage. We're going to practice cooling down those liquid hydrogen and liquid oxygen to these cryogenic temperatures, which means they are freezing cold. And then we're going to turn on all the computers and then turn on all the engines and make sure the entire thing works correctly. Once we do that, we're going to go ahead and take our core stage and we're going to ship it over to Kennedy Space Center in Florida. We're going to attach on the solid boosters, attach on the exploration upper stage, attach on the Orion, and off it goes to the moon.
Now, you talked a lot about igniting propellants. You talked a lot about, hardware and the fact that computers are going to play an integral role with respect to the Space Launch System. Student online has a question here which coincides and relates to the things that you were basically saying. So as a more specific question, what advice would you give to students here when it comes to the different paths or the different specialties inside of aerospace engineering?
That is a really good question. I like that one. So aerospace engineering, at least at Cal Poly where I went, was split between astronautics and aeronautics. So the astronautics students would learn how to build rockets, and the aeronautics students would learn how to build planes. Now, for the first, so throughout high school, even if you know you're going to be an aerospace engineer, your classes are the same. For the first 2 years of undergraduate, even if you know which type of rockets or planes you want to build on, classes are the same. So your decision only really comes towards the middle of your college career. And that's where you start learning. If you're aeronautics, you start learning about wings. You start working in the wind tunnel. You start practicing figuring out what is supersonic flow and that kind of stuff. And then if you're an astronautics kid, you start learning about orbits. You start learning about electric propulsion. How to decide between the two? It's really just being exposed. It's really just saying, what kind of stuff do I want to work on? Do I like working with rockets, which are larger but don't fly as often? And do I want to work with planes, which are much more of a production? We make lots and lots of them, but they don't go as fast as rockets do.
Okay, excellent answer on this end. Um, so the Space Launch System is a very big project. It has a lot of moving parts. So you spoke a lot about the differentiations with respect to aerospace engineering, but what do you actually work on specifically?
So I get a really cool job. My job is called transient analysis, and it's my job to turn on the engine. So it's my job to figure out how to get the fuel and propellant into the engine at just the right rate and turn them and light them on fire just the right way so that nothing breaks and the engine turns on every time. It's really exciting work. But I don't get to like play with the knobs. I don't like. I'm not in the test center going, we're gonna turn it on now, because we turn it on in under 5 seconds. I am not that quick. I am not speedy like that. What I do is I do a lot of modeling and analysis, really detailed analysis work to understand exactly how all of the parts of the engine are going to work when we try to turn it on. And then it's my job to tell the computer exactly how to turn it on. Tell the computer to turn this knob, then turn that knob, then turn this knob, then turn that knob backwards in order to turn on this engine reliably, safely, over and over again for our testing purposes.
Okay, excellent. Now, earlier in the program, I spoke a little bit about the engineering design process and why testing is such an important element to the engineering design process. So, why are the green run tests so important? And how many times do we actually test?
Yeah. So I'll bring it back to actually when I was building my solar car. We were a lot smaller project, only like 30, 40 people. And testing was so important. It's the most important thing for us. We would get out to the field and we would test and immediately find out something very important about the project that we had to fix. If we had gone for the record that day, we would have never completed it. We wouldn't have gotten the car turned on. Through testing, you find all of the little details. You find all the variations that your brain can't think about, even the best we try. Now, when we are testing the SLS, we might find things. We're hoping to be able to test the whole system, really figure out how to work with it, how to turn it on efficiently, how to work with moving this massive stage around. Every single component on the entire SLS is tested by itself. Then it's put together. So every component of my engine is tested on its own. Then we put the engine hull together and we test the engine in what's called an acceptance test. We turn the whole engine on. We run through all the checkouts. Then the core stage is going to be our full test. So we test every part as it comes in each and every time. And then we test the entire thing to make sure it's going to work perfectly, which I am 100% expecting it to.
And I know in terms of your position and everything that you aid in terms of igniting and starting the vehicle or the core stage, at least during the green run test, that is. But we're talking about this marriage between hardware and software. Can you just talk a little bit more about what is the role of software engineering at NASA? We had a student ask that question.
Yeah, that's a really good question. So software engineering is really, really, really important right now. There are so many things that are so complicated on a rocket that you cannot do manually. There's no way we have time for the Orion astronauts to be able to do things that a computer could. And even if they do it, they couldn't. All they would be able to do is tell a computer to do it, because every single engine is called gimbaling. So every engine can move back and forth and forward and backwards. Even the solid boosters on the side, they have thrust vectoring on them. This enables us to turn the rocket. And there's no way a human could pull, like the old planes when we started building planes. You had a lever that you would pull to move your wings, to move your wing surfaces. You can't do that with this. We have complicated hydraulics, kind of like excavator type machines that move the engines back and forth while we're flying. So software engineering is really, really important. It's also really important because you're flying humans on top of it. And it's very easy to, there's a lot of complicated things going on. And so you need to manage all of those things in the software. Software engineering is actually pretty critical for SLS.
Wow, that's terrific. So let's just digress here for a moment on this end. You're talking about the people, the team spirit behind the operations. We're talking about the management. How important is teamwork in your job with respect to aerospace?
Well, it is so important. For me, it's one of the most important things. Everyone, when they are talking about like Aerojet Rocketdyne or NASA, they always talk about the people they're working with. Everyone who says, if you ever ask anybody, do you like your job? They always say, I love my job and I love the people I work with. It's so important just because we're made to be people who work. Like, one reason is because we like to work with people. But secondly, no one can build a rocket like this by themselves. There's no way. It's impossible. No one can even build an engine, let alone even some of the parts of the engine by themselves. There's not a single person who knows everything. You have to work in a team in order to complete an amazing cast like this. And so that's where you really learn. Like when I was in college, I had a thesis team. So I had 3 different people on my team that I had to work together with, 3 different advisors. When we worked on wind tunnel projects or when we worked on projects for smaller companies, we got to work on specialized teams, spending all of our time together, learning how to communicate effectively, how to share responsibilities, how to get over disagreements and figure out what the best path going forward really is. Teamwork is one of the most important things in my book, especially when it comes to aerospace engineering.
Absolutely. And you're talking about the love for technology and the love for people, which is very important. Speaking of which, in terms of people, who are your role models? Who had an impact in terms of you and your life?
So I have a lot of important role models in my life that I can think back on. Just a few of them. Let's see. My high school teacher in calculus, Mr. Stebbins. He was really instrumental in getting me excited about the math that was really hard. He was really excited about it, and he was really good teaching, making sure we worked hard, but really was able to learn and weren't too confused by ourselves. My advisor in undergraduate for physics was Dr. Deitz, and he taught me a lot about the power of communication. He taught me a lot about the power of hard work. He taught me a lot about how to teach. I had an advisor in my master's program called Dr. Amelia Gregg. She was also really amazing. She helped me get to have the confidence to go work in Japan for a whole quarter and work on satellites in Japan, in a country I don't know how to speak the language. She had taught me the confidence to complete my thesis, 140 pages, and she really inspired me to be a good aerospace engineer. And then my dad and grandpa, they're always good inspirations as well.
That is awesome. Now, we talk about NASA, which stands for the National Aeronautics and Space Administration. Question here from a student: is aerospace engineering the same as aeronautics?
So aeronautics is a part of aerospace engineering. So some aerospace engineers do aeronautics. And aeronautics is really just figuring out how wind flows is the easiest way to think about it. It's fluid flow over items. So aeronautics engineers include figuring out how to build wings, figuring out how to build the shape of the rocket, figuring out how to work on turbine blades, which are moving through gas. That's what aeronautics engineers get to do.
Okay, great. Another student had a question with respect to actually becoming an astronaut. They asked, well, are there any specific degrees needed to become an astronaut?
So I think it's highly recommended that you have a degree in STEM. That's at least my understanding. And it's very important that you show that you know how to work in a team, that you show that you know how to work hard, and that you show you know how to learn. Astronauts that I've met are like the most humble people. For us, they're like superstars. And for them, they're coming down to my job and they're talking to me saying, what do you do and how do you do it? And I'm like, the astronaut wants to know what I do? This doesn't make sense. But they know how important everyone's job is. And they are kind of the unofficial leaders of our teams, or at least the unofficial mascots of our teams, because we're doing all of this for them. We're doing all of this work to keep them safe and healthy and get them to space. And I think they understand that and they know how important that is to them.
Yeah, absolutely. I totally understand with respect to that, and looking up to many of the women and men who are astronauts and who actually put their lives on the line in the name of science. So here for a moment before we run out of time on this end, can you tell us about maybe a career challenge that you may had to overcome to where you are today?
Yeah. So I would say one of the biggest recent challenges I had was my master's thesis. So when you graduate undergraduate, sometimes you go and do what's called a master's program. And that master's program, a lot of times you have to write a paper. So you do a project and then you write a paper about that project. And then you take that paper and you send it off to experts and they come to you and they review it. So you have to defend it. So you have to stand in front of a room and say, I did this correctly and I know what I'm doing and I made significant advances. I don't like writing. I don't enjoy writing. It is not the thing I do. I would rather be put in front of a computer and code all day. I actually coded my writing part of my thesis because of how much I like coding. So writing cool. 140 pages took a lot. It was a lot of hard work. I had to sit down and really grind and stare at my and understand like how to work really hard. It was one of the biggest challenges I went through recently, and I'm really happy with how it turned out. I definitely could have turned something in that I wasn't happy about, but like I turned it in and I looked at it and I was happy with what I produced, which I was really proud of.
That is awesome. And I'm sure your parents are proud of you. So it looks like we're just about out of time today. But before we go, we have a student challenge for you. So we're actually challenging you to build a multi-stage balloon rocket. It's the Space Launch System Educator Guide. And you will actually get the opportunity to design and build a multi-stage balloon-powered rocket to demonstrate how rockets can actually achieve greater distances using the technology of staging. So you can see the link there to the activity in the chat window, and that's going to actually take you to the Next Gen site so that you can actually begin completing your amazing spacecraft. And we actually hope that you will share your work on this activity with us here at #NextGenSTEM. Two more things before we wrap it up today. I want to say thank you so much to Dominic Lundy for coming on our show today. It was great talking with you and learning more about the great work that you do. Lastly, join us for our next Stars on November 4th at 2 p.m. Eastern, where we're actually going to learn more about launch vehicle trajectories. How cool is that? Thank you all for attending today. Please don't forget to subscribe, and we will definitely see you soon. Take care, be safe out there, and have a great day. Take care.
Going to space is awesome. My first flight was on the space shuttle. You get into the vehicle, you're all strapped in. You know, we have the countdown timer that's going on. You get to 0 and the launch begins. In your mind, you're thinking, I can't believe this is actually, it's the coolest experience ever.
Hola, Joseph. ¿Es tu padre?
Hey, Pops. It's good to hear your voice. Thanks for the support. The launch was awesome.
When I look back to who inspired me, it started with my grandfather. He actually had the old films of the Apollo missions that we would watch. I've been fortunate that I've had those mentors that have supported me and motivated me to be where I am today. I was born in Southern California, reading, playing sports, Enjoyed being outdoors, spent some time in the United States Marine Corps Reserve, was a U.S. Peace Corps volunteer, did a lot of different jobs until I found the one that I felt was the most important job on the planet, which is being a school teacher. It was one of the jobs I never thought I would leave until I was given this opportunity to become a NASA astronaut.
NASA astronaut Joe Acaba making his third flight into space.
I've had the opportunity to go on 3 space missions, and I've spent about 306 days in space to actually walk on the moon. For me, to have that as a possibility is just incredible. This is our next step to explore places we have never been before.
All right, NASA family and friends, our first astronaut, Kayla Barron.
I think the thing that's most important to me is just the inspiration of exploration. I think we all have this innate sense to explore, whether you're the one who actually gets to step on the moon or not. I think it changes all of us to know that we can actually do things that would be unimaginable to the generations that came before us. 9/11 happened 8 days before my 14th birthday. So I was in 8th grade, and I was really inspired by how our country responded to that really tragic event. It really, now, here I am.
You're one of my favorite people.
For me, every time I have an NBL run or every time I do a practice spacewalk and you get in that suit, like we call it the EMU, and feel the gloves go on, feel the pressure build, feel the fan start to flow and the air start to come over the back of your head, and you realize, like, this is it. That's when it really strikes me that this is actually not a dream. This is actually happening.
I'm Raj Achari. I go by Grinder. I grew up in Iowa and went to the Air Force Academy and then MIT, and then was an Air Force test pilot.
If I ask my mom, she definitely has memories of me as a child talking about being an astronaut. Well, I always knew I wanted to do something related to aviation, but at the same time, I think I also started to tell myself it wasn't really possible because it was just something to get let down from. Every phase of my life I had doubt, whether it was at the Air Force Academy and wondering whether I could survive basic training, whether it was when I was at MIT, or even pilot training, failing check rides, and thinking, again, maybe I'm on the wrong path. But I think in all those events, been blessed to have a supportive family, supportive spouse, supportive mentors and leaders who helped me at the time realize, like, hey, these are setbacks, and you get better by tackling those head on. For the Artemis mission, they're not just PowerPoint slides. They're actually metal is being bent, shaped, formed to build the things that we're going to use. And as a test pilot background, this is a dream job to actually be involved in all of this.
Now looking back, I would have told myself, hey, just pause and appreciate what's actually happening around you and the magic of the moment that you're in.
Newton talks about, standing on the shoulders of giants. Now, I'm definitely not a giant, but if I can throw a little stepping stone out there, that would be my goal. My name is Rajachari.
That's awesome. Very good, very good. I like it. I like it. Grab your hand.
Oh, what am I doing? We're videotaping this?
Everything you're doing. Keep doing.
Ladies and gentlemen, our newest astronaut, Matthew Dominic.
I think if you boil it down to it, I'm a father, a husband, and an explorer. For my whole life, I've always wanted to explore further. I didn't exactly know where I was going to go at any one time, but I always knew I wanted to go further or faster or higher. I remember as a kid going to air shows with my dad and just looking at airplanes, and I wanted to understand it, and so it was just drawn to it. Every air show I went to, I wanted to go get in that airplane.
I grew up in Wheat Ridge, Colorado. Went to the University of San Diego for electrical engineering, and went to Naval Postgraduate School as well, Naval Test Pilot.
It's certainly a sacrifice for family and friends. Being in the military, we would go on deployments and lose contact with them, and they understood the risk that we were taking. You think about the immense responsibility put on you at times. You don't want to let the world down, but it's about pushing humanity forward and keeping America safe. On you at times.